All right, everyone. Thank you all so much for waiting. The stream has finally been set up on YouTube, and we're good to start. All right, everyone. Thank you all so much for waiting. The stream has finally been set up on YouTube. Sorry, 1 second. Okay, so just to ensure that in the first rounds that following the order of the presentation, Maxwell's demons will be presenting first. Schrodinger's cat girl will do the reviewer jobs, and the Shroomsky will do the opposition. So everyone is here, right? Okay, are all the jurors ready as well? Yeah, sorry for the waiting.
Yep.
It's been a long time.
Yep.
Okay, so for the participant, you should be able to see the timers in our volunteers camera as usual. And yeah, I guess it's time for you all to present. So for Maxwell Demons, the problem they will be presenting is, sorry, kind of. Okay, the problem they will be presenting will, where did it go? Sorry. Uh, the problem they will be presenting should be the sound versus fire. Okay, and so now we could. All right. So take your time. 1 minute timer starts now, and then you should be able to start presenting your slides. All right, let me know when you're ready, and then we start the timer.
And here are my material lists. Note that the speakers are built by myself. It's DIY. So here we can then here. So here's a phenomenon explanation. So due to sounds being a pressure wave, just to cause disturbances in the air, my hypothesis on sound being used to put out fire are the disturbances like blowing move the air to here's a phenomenon explanation. So due to sounds being a pressure wave and lower overall temperature of the affected area, which does not allow the combustion to continue. To investigate this phenomenon, we'll be modifying the area of sound application, so this cone opening width, the distance of sound traveled in the cone, as well as the amplitude and frequency of the sound. Just a repeat of what we stated before. So here's the Kenner diagram, right? We're not going to go that much into detail with the chemistry, but the liquid wax goes up here, it gets vaporized, the radicals react with air, therefore forming a fire. So here are my experimental setup. So here's my experimental setup. Here's a DIY speaker. Here's the LM386 dual bridge amplifier circuit I built, which is linked to the speaker and linked to the candle. And we're going to be changing intensity, the cone, as well as the frequency of sound to see how it will affect the time it takes to put out a flame. Here's my theoretical model. So here are my theoretical models. So the first model is constant 80 Hertz, yet we're changing amplitude. Here are the assumptions we're going to make. So we use the constant frequency with varying dB. So the frequency is just going to stay perfectly constant. Has no energy loss due to the aluminum foil insulation, right? In the cone, the sound traveling in the cone has no energy loss. The candle flame is constant height, and the candle has the constant distance between cone opening and the candle or the flame. Here's my geometry. So frequency will be the same. Assume that the candle stays at the same height. We're going to be altering volume. Cone will be changing, and just aluminum insulation, which we could then assume the energy loss is minimal. Basic principle. So here is the basic principle 1. So over here is just using dBSPL, so sound pressure level decibel, and this is going to aid us in our experiment further. Here's basic principle 2. And instead of using the max pressure, we're going to be using a root mean squared pressure, which will give us a better result as it's an average. And here's the formula we're going to be using. It's a 2. And here's the third basic principle formula, which is this. And we're just going to have a derivative of the displacement of air particles over here. So pressure equals to density of air times the velocity of air in the medium times the velocity of the air particle caused by the sound. And for a sine wave, because it's sine wave, right? It's going to be the max displacement times cosine of angular frequency times time. Now, we derive this to get velocity, and this is our velocity term. So by combining these together, we rearrange into intensity is pressure squared equals to this. Substitution into this gives us the velocity of air equals to maximum displacement times angular velocity. or angular frequency. But since sine 90 at max is 1, we could cancel out the sine term, therefore giving us this formula. And by rearrangement, and from the formula I stated earlier, we get this formula. So moving on, combined solution. By substituting all values, by expanding all values or all variables, we get this, and we see that the air displacement is inversely proportional to frequency, but proportional to intensity, and velocity is also proportional to intensity, but has nothing to do with the frequency.
Yeah, what's poppin', guys?
So
Sizzle
my
here, and
experimental
this
verification. This is using the 7 centimeter, 6 millimeter opening cone, and as you can see, this is a exponential relationship going down. So as sound increases, the time it takes to put out the flame decreases exponentially. And here it's the same thing with the with the 12 millimeter, so bigger opening of the cone. And by looking at this, this matches pretty good with the theoretical formula we put up. And by graphing it, we see it's an exponential increase in the air displacement velocity as decibels increases. And over here as well, this is the air displacement as decibel increases. So as you can see from earlier, the correlation is pretty strong as it's seeing that the velocity and the sound displacement or the air displacement increases exponentially while the time decreases exponentially as you increase the volume. So model B will be constant decibel, no energy loss still, but we're going to be experimenting with different frequencies. Here's my geometry, same thing. We're going to be using the same two cones, but instead of changing amplitude, we're going to be changing frequency. So as over here we stated. So assumptions. Here are the key assumptions I bolded. The other ones are just sort of repeats. So there are no energy loss from cones used, because that's the most important one. The flame dimension stays constant, the flame temperature stays constant, the velocity of sound stays constant, and the medium in which sound travels through stays homogeneous. So the basic principle, this is already stated before, intensity equals to square of pressure over 2 times the air density times the speed of sound in the medium. Here's the other basic principle we stated also earlier. And by combining the solution, we get that the displacement of air max equals to this. And by deriving this 2 times, we see that the acceleration would be y max times the w terms cancel out. So acceleration max will be related proportionally to frequency, because w is just 2 pi f. So here's my experimental verification. So as you can see over here, the best frequency it takes to put out flames is around what I got was a 60 to 70, so that range. And by graphing our formula out, we see that we have an intersection of both sound displacement and acceleration at about 50. So this matches pretty well with my data, and this also shows that as frequency goes up, the sound displacement will go down. However, acceleration of air particles will go up, as well as energy. So there is a sweet spot I found where the frequency will both allow air displacement and acceleration of particles to stay maximum, which gives you the lowest time. So as I mentioned before, about 50. So my last theoretical model, model C, is the changing diameter of the cone. And we're going to say that there is, and for the changing diameter, there's still no energy loss because of aluminum insulation. So same as before, however, the cone will have no insulation, and the height will be investigated also to view the effects of height and energy loss. But when we're investigating the cone opening width, we're not going to be investigating energy loss. However, we're just going to assume that there is no energy loss by replacing the inside with the aluminum. And now we're going to be using constant 80 hertz with changing amplitude. So assumptions. The sound intensity and volume loss for both cones are the same. Both volume frequencies of sound remain the same. Candle flame heat and dimensions will remain the same again. Cone density is constant and homogeneous throughout because I use a 3D printer. It cannot be perfect, but we're going to assume that's perfect. So basic principle 1, we're using the continuity equation, A1, which is air rate times the speed of sound equals to the flow rate. Basic principle 2, maximum pressure equals to density times velocity of the sound times the flow rate. So combining the solutions, we get this. And since rearrangement, we get maximum particle velocity equals the flow rate over area. And by equating those two, we see that the pressure is inversely proportional to area, which is expected, right? P equals to F over A. Smaller the area, the more the pressure it is. So this is also seen in my experiment as well. Now, experimental verification. I'm not going to show the energy loss, but I'm going to show the hole opening differences and how it affects the time it takes. As you can see over here, the 12 millimeter opening hole bigger than the 6 millimeter opening hole. You see that it takes a little bit more time to put out the flame versus the 6 millimeter hole, which takes less time. And this is expected because more pressure, right, equals to less time as it is exerting more energy and I guess more exerting the energy more effectively to the flame. So here are my key parameters. Key parameters are are that I change cone opening width, loudness, frequency, and cone height, and they all affected the time it takes to put out the flame, the velocity of air, displacement of air, except for frequency not affecting velocity, which is expected from a longitudinal wave. So over here, as you can see, the correlations are pretty strong with the key parameters I've varied. However, just frequency just doesn't affect velocity as, right, it's a sound wave. So in conclusion, by altering the amplitude intensity of sound, the frequency of sound, as well as the sound concentration device, the cone, and keeping the flame constant, the parameter of how sound can put out fires can be investigated. The most important two and the volume of sound. This is due to the volume increasing particle speed and pressure of sound, therefore increasing wind speed, and the cone width allowing higher pressure. So it was observed that increasing the sound volume while keeping the same cone shape resulting in a positive correlation with wind speed as predicted by our formula. This displays that higher sound intensity has greater extinguishing effect by generating greater air movement, decibel pressure, and velocity. Additionally, when varying the volume and comparing the results across different cone opening widths, it was seen consistently that effectiveness of sound in extinguishing the flame is inversely proportional to the cone's opening area. This aligns with the combined formula, which indicates that as the opening area increases, the pressure and wind speed decreases, reducing its extinguishing effect. Here are my references. Thanks for listening. And before I end this, I'm just going to go to the appendix. These are the key points and how I'm going to improve this experiment if I had more funding and given the chance. And lastly, here are my tables, and this is the end of my presentation. Thank you very much.
All right. Thank you, Anthony. And now it should be a 2 minutes quick fire round for the opponent.
All right. Thank you so much for your presentation. So just to clarify, you used a modified problem statement. Is that correct?
Yes, I used a sort of modified problem statement to fit into my experiment better because I don't have the funding, right?
Okay. Anyway, yeah, thank you. Next question. Did you analyze how the speaker orientation kind of affected flame extinction and whether candle alignment kind of produced which effects?
Well, I did sort of look at that, but I didn't focus on that much because I believe that the cone opening width is actually a very big I guess, impactful on the time it takes to extinguish. But I do notice that whenever the cone opening width is not aligned, right, you can model the sound out as a sphere. And as a sphere, if it's not aligned, it's going to be less effective to put out the flame.
Right.
What I observed.
Where did you put your decibel meter? Because I believe I don't see it in the experimental photos.
Oh, sorry. So what I did was I had a candle. And I didn't use a decibel meter. I actually used a decibel app, which is the same thing. And I put it where the flame is supposed to be. I took a ruler, measured it, and then after that, after recording the decibel of each, because my MacBook uses bars, so 1 bar, 2 bar, right? You're familiar with that. I tested for each bar, and then after that, I put the candle back, and then just used the same.
Okay. We do actually recommend calibrating the decibel.
Yes.
Next question. Sorry.
Repeat that. Thanks.
Oh, okay. Oh, sorry. We'd recommend calibrating the decibel app because a cell phone may not be necessarily accurate.
Yes.
So, sorry. Next question. Did you investigate any room acoustics and how did you minimize effects such as room resonance?
Well, since the sound was so concentrated to the flame, I didn't believe that there was any room acoustics, but I didn't really look into how the room would have affected sound. No, I have not done that.
Okay, I see. Let's get standing waves or only traveling waves?
Could you repeat that?
Oh, did you investigate standing waves or only traveling waves?
I'll only investigate sine waves for my experiment because
Okay, done.
because
Time's
I
up.
was not able to produce.
Sorry, time's up.
Sorry.
Okay. All right. So next round will be a 3 minutes preparation for the opponent, and time begins now. Last 10 seconds. The opponent should get their slides presented now.
Hi, can you see my screen?
Yes.
I can.
Okay. In that case, I'll start in 3, 2, 1. So, hello, my name is Ethan, and I will be opposing problem D, sound versus fire. So the problem statement tells us that a small flame can be put out by sound, and it asks us to investigate the parameters of flame and characteristics of the sound that determine whether the flame will be extinguished. So, going through the tasks, we thought that the first task, which was identifying relevant parameters affecting flame and sound, was quite well done. The second task, like creating an experimental setup with reproducible results, we thought this was quite well done as well, and we thought the use of the cone was also quite interesting and a very good addition to the experimental setup. The third task, being the qualitative explanation, we thought it was limited because it could use more exploration into, not like super deep, but into like the effects of combustion, like the flame itself, how to characterize that. Then the fourth task being modeling the phenomenon quantitatively, we thought that this was also sort of limited because most of it was focused on characterizing the velocity of the airflow and the disturbances. And we thought possibly more could be incorporated in order to make the quantitative more complete. And the fifth task, finally, comparing experimental with theoretical. We thought this was limited, and there was only one parameter compared with theory, and there were like not as many graphs. So just to summarize the report, first, the reporter gave a qualitative explanation of the phenomenon. Secondly, presented their experimental setup. Third, presented their 3 quantitative models. And finally, provide some experimental verification. So overall, we thought that these things were quite well done. First being the impressive use of electronics, engineering, and setup, especially the use of PCB design. And as I mentioned earlier, like the cone. Secondly, the use of multiple models and varying some parameters. And that was mostly focused on investigating the airflow. Third, we thought it was quite like they compared experiment with theory. Finally, identified some key parameter interactions and the correlations between them. In terms of next steps, we'd suggest first a better, as a fundamental starting point, a better or improved qualitative explanation, because there wasn't really a rich explanation of combustion. And I think that could have been better explored, or I think it was kind of rushed. Secondly, there was no investigation into the type of fuel source and whether if it's constant while the candle's burning, and how that incorporating that. Thirdly, the theory could incorporate some more. It was a bit limited, and I think we'll be expanding more on that in the discussion. The fourth being further explanation of theory experimental discrepancy, because there were some deviations across graphs. Fifth and finally, varying more key parameters, such as type of wave, for example, using sawtooth, square, etc. So now in terms of the discussion, I'd like to discuss first the errors in experimental setup. Secondly, discrepancies between the theoretical and experimental. Third, varying key parameters. And yeah, that's it. I think we can move on to the discussion. Oh yeah. Could you share your slides, please?
Of course, I'll do that now. And let me just play from start.
Okay, so just the first question, just general question. Did you account for the frequency response of the speakers? Because for a given frequency input, the speaker, the efficiency of the speaker changes, and so
yes, of course I have. So what happened was when I was actually starting this project, I bought the LM36s. They were able to actually handle a load of 32 ohms of impedance of the speaker, and the speaker I'm actually currently using is 6 ohms with the response of 20 hertz to 20 kilohertz. 20,000 hertz, 20 kilohertz. So before buying everything, I do check, because money's tight and I don't want to waste money also. So
okay.
Yes, we'll check.
So I don't believe impedance.
You cut out.
Oh, sorry. I don't believe impedance affects the frequency. Yeah,
Yes.
Yeah, I don't believe impedance affects the frequency response, because we're talking about non-linearities in the frequency.
Yes, of course, but it will affect the sound quality output, as well as if the chips could handle the speaker. So that's just what I put up there.
Okay. On that note, did you characterize the frequency response of your decibel meter?
Frequency response? No, because it was my phone. I didn't have that much money to get a decibel meter.
Okay, I mean, I'm echoing my statement from the rapid round. I think we'd recommend getting a decibel meter, because it kind of only costs $10 anyway.
Yes, yeah. But
then the second question, I think it kind of got cut off from the rapid round, but did you investigate standing waves or only traveling waves?
I only investigated traveling waves, because I was only able to find a program that could do sine waves actually.
Okay. I think we'd recommend investigating traveling waves, as well as maybe the use of multiple speakers, 2 speakers. Cool.
Yeah, of course, yeah.
Next question, did you characterize your fuel source in any way?
Excuse me, could you please repeat that?
Okay, did you characterize your fuel source in any way?
Oh, fuel source, yes. It was a wax candle, right? And I did learn, I was able to learn that the wax, sorry for rushing through this, but first of all, in order for fire to exist, you need fire triangle, fuel, oxygen, and heat.
Yeah.
How the candle works, right? You light the wick, it melts the wax liquid travels up the wick, becomes into a vapor, radicals and recombination with oxygen or the radicals itself, which could create the heat necessary to become a flame. So that's I did investigate that. That's why I chose to only use one candle, and the one I used was the ones I could find from IKEA, like those like little round ones, those white ones. Yeah.
So do you think like the burning output would be completely constant then, like using your candle?
So I did think about this actually, and I was able to actually calibrate it by first of all trimming the wick, and second of all looking at the wax depth. So when you mount the candle, right, you have like a giant pool of wax, molten wax. I did look at like, do I have to pour some out? Do I have to add some in? Do I have to keep the wick? Do I have to cut the wick? Do I have to use a new candle? I looked at that always.
Okay, did you observe like, did it change between like trials or throughout trials?
No, because I was using a new candle every trial.
I see.
By measuring, yeah.
That's good that you like use the control like to make the data more effective.
Yes.
I think in terms of like fuel source, we'd recommend like using different types, such as like a gas flame. I think that could to look into.
I was thinking about using a Bunsen burner, but
Yeah,
I don't
it could be more controllable.
I have a gas line, so I can't sort of investigate how it will affect airflow, right? I can't like, I don't have a Bunsen burner to aim the pour at the air intake and just shoot sound waves at it. It was some material issues.
Okay, yeah, thank you. So could you go to slide 18?
Slide 18, of course. Come on, okay. 11, 12, 13, 14, 15, 16. Here you go.
Okay, so this is a fit curve, correct?
Yes, a line by fit curve.
So I was just wondering, so what type of fit curve like did you use and like why?
So I used a log, well, I will call it exponential, but it was also log fit curve.
Right.
And I wanted to use log because, as you know, right, from earlier, we did say that a decibel as power increases through a log scale, or the pressure actually increases through a log scale because I use dBSPL. And to use the log scale, it would probably fit the data better. And using a line of best fit, you do see it's a exponential form, which you could convert it to log scale, log base.
Yeah.
So,
I mean, the trend, like, it kind of looks like it's there, but it doesn't look like it's like quite a good fit. So maybe we'd recommend like also like getting more data points to see like a clear trend, as well as like maybe transforming to like absolute intensity instead of like just using like decibels. So yeah.
I totally agree, but another problem I was facing was I didn't have that those expensive high-tech slow-mo equipment. I was able to use the app on my phone to capture at modified frame rates and multiplying that to get the original speed it takes. So that was the problem I faced.
Yeah. Just one more thing. Sorry for like bombarding questions on this one graph, but like I use like error bars. So like, how many trials approximately did you do?
I did 3 trials, and they were actually somewhat consistent with the data I was receiving.
That sounds good. Okay. Could you go to slide 23?
Of course. Slide 23. Here you go.
Cool. So based on this setup, like, would you say your sound is collimated?
Could you elaborate what collimation means?
So basically, it's where like when you're producing, like the direction of the airflow is parallel. Part of the.
I would say so because from what I remember, this cone had a internal aluminum foil on it, and it was sealed. Therefore, the only exit of the sound was through the cone opening.
Okay, so, because it's only coming.
You cut out again.
Oh, sorry. So, can you hear me? Okay.
Yes, of course I can.
Okay, so it looks like it only came from like a point source, which means that it's not collimated. So it might react at the end. So actually, we'd recommend using like a setup that generates a collimated sound, which is like easier to model. Like instead, you could probably fit a cylinder to the diaphragm of the speaker, and that might generate better results.
Yeah.
And also, I just want to point out like the non-collimated means like the pressure varies across the flame in multiple dimensions, which makes it more complicated to measure.
Yes.
Yeah. Also, you mentioned you used aluminum. So could you clarify like what the aluminum insulation is for?
So according to many sources, aluminum being a sound insulator is about 85 to 90% efficient at trapping sound, or actually reflecting sound, at being an insulator.
I see.
So to use aluminum inside on the inside of the cone, it allows the sound loss, which sound, right? It's energy in form of pressure waves loss to be at a minimum. So I don't have to really do the necessary calculation to see how much, I guess, energy was lost to the cone, because the cone is printed from a plastic from the 3D printer. So
Well, it's very interesting, and we didn't actually think of this in our setups. And yeah, we'd like to commend you on that, like your experiment.
thank you very much.
Yeah. Could you go to slide 36? I believe this is like in your third model.
Yep, of course. 2, 3, 4, 5, 6. Here you go.
Okay. So what do you think the main causes of the bad alignment between theory and experiment is?
So are you talking about the first data points, right?
Yeah.
So this is actually a very big issue I was facing, and I'm gonna put in symptoms. The LM386 and the speaker bot were crap, right? It takes a few seconds or it takes a few trials for it to actually get a consistent sound. So the first one you can actually count as outliers, because the first one was making a raspy. Nearing the end of the experiment, when the speaker was warmed up, it will make an O sound. But in the beginning, when I wasn't using it, it made an E, like it was a very bad quality. So that's why there might be an outlier, and due to it not being more acoustic, not being more uniform, that could have affected the time it takes to put out the
I
flame.
see. So it does it does sound like your speaker may have like harmonics. So we'd actually recommend like using an FFT to characterize this kind of response.
Could you explain to me what an FFT is?
Okay, basically it's like a fast Fourier transform, and you can analyze for different like frequencies like peaks.
Oh.
So it's like a very useful tool to analyze it. Yeah. Anyway, do you have any like closer up images of like the later data points, because it's like hard to compare theory and experiment for them?
I don't think I do. Let me just check. Here are my data points. Go back. Here, does this fit, or do you need way more? Closed in.
Okay, sure. I think. Oh well, I mean, we can't really like see them. It's fine though. Yeah.
That's the problem. Yeah.
Did you fit any like constants into your theory?
Yes, many constants were fit in, such as the air, right? The speed of air in the medium, and since I was doing it in the same place with the same temperature, because there's a thermometer outside, or there's a thermostat outside, I was constantly checking, as well as the, I guess, humidity. And I wouldn't think humidity would change that much overnight, so I was just doing the experiment in the span of like 3 days, just getting everything done and then plotting it. So
Okay.
I don't think the experiment, the environment changed that much. So
I see. Thank you. I think we're out of time.
All right, cool. So now will be a 1-minute session for the opponent to summarize the discussion. Yeah, you may start anytime.
Okay, yeah. In conclusion, we had a very fruitful discussion with the reporter. Specifically, we talked about certain aspects of their experimental setup, such as their speakers, and like kind of improving on modeling things like the frequency response of that, as well as like using a decibel meter. We also looked at like the effect, or like briefly mentioned the effect of varying different parameters, like using different waves, what type of waves they used, and also like fuel source, whether or not like the candle burning rate was constant in that sense. We also looked over the experimental graphs, assessed like theory experimental fit, discussed possible reasons for deviations in the theory, and clarified them with the reporter, and then also discussed the component of the collimator in their setup and how maybe it'd be better to use like a cylinder to be able to like make the sound go like in a parallel direction, and like varying parameters. Yeah. And thank you so much.
Great. So now will be a two. Sorry. Now it's time for a reviewer. My bad.
Yeah, so my first question is for both of you. What would you consider the impact of pressure on the reaction rate be? Because as the reporter mentioned, flame combustion undergoes a radical reaction, which means that the rate of reaction is proportional to the concentration, which is proportional to pressure, right? So how would you characterize that change? Yeah, go ahead.
Actually, before, could you repeat the question? It kind of cut out.
So essentially, since as the reporter said, it's a radical reaction that causes the combustion. How would you characterize the change in pressure on the reaction rate? Because the rate of reaction of radicals is dependent on its concentration, which is dependent on pressure. Go ahead.
So I would say that through my presentation, if I may present my screen, may I?
Sorry, we don't have a lot of time, so
I'll just keep it simple. So pressure, right, is a big factor in air displacement and air acceleration and velocity. So by looking at pressure, how it affects, you were saying the concentration of the radicals, right? By looking at how pressure will affect that, you could just take pressure related with air velocity or air displacement and see the change in displacement, which is crucial to change of concentration of the radicals. I believe that can be a pretty good way to,
I think I'll answer next. So we actually think the change in pressure for sound is like very small. Like theoretically, it should like be less than 1% of atmospheric, like only a few pascals. So pressure, I think, should not like have a large impact on reaction rate. And like also the main use of pressure is to induce air movement. So yeah.
Awesome. So my next question is for a reporter only. You mentioned that one of your assumptions was that heat was distributed evenly, but we know that the heat is not in fact distributed evenly because only the reaction occurs on the outside where there's oxygen. So why would you say that that's not relevant?
Could you repeat the last part again?
Well, why would you say that that's a reasonable assumption that it's consistent in temperature throughout the flame?
So you were saying that the flame only reacts with the oxygen outside, right?
Yeah.
So was that your point? Yes. So since it was reacting to the outside, right? And the pressure wave hits it. What I would like to sort of look at is that I didn't have a temperature meter, but because there's disturbances in the air, right? The air particles will undergo more collisions with each other, and I guess equalize with the entropy of the room. So this in turn could be a factor in putting out the flame by equalizing the outside of the flame's temperature with the room, with air room. I do note that in previous presentations, I have been rebuked for mentioning this because because according to other presenters, the air's insulation conductivity of thermal energy was too low. But
Okay.
I would like to say that the air isn't stationary.
I think we're at time. Sorry.
We're out of time. So, all right. So now it's time for the preparation of the reviewer. 2 minutes. Take your time. You guys still have 1 minute of preparations, but if you are ready, just let me know.
We'd like to take our preparation time, please. Thank you.
Okay.
Okay, I would like to start in 3, 2, 1, now. So my name is Jeff Sun with Schrodinger's Cat Girls, and I will be reviewing problem D, sound versus fire. So we already know the problem statement. So the tasks that we need to accomplish here, which have been gone over, are identify the key parameters, qualitatively and quantitatively model the phenomena, and create an experimental setup that correlates well between the theory and the data. So for the report, they start with a theoretical analysis based on the frequency, intensity, and the focus of the sound. They use that to derive the pressure change and displacement and finally model the extinguishing ability. And with their experiment, they measure the time to extinguish, they determine the trends of the data, and they qualitatively saw whether the graph shape matched up with the theoretical analysis. So some things that the reporters did well was their experimental setup, their measurement, their models, and their good assumptions. While their possible next steps would be some more clear analysis and some investigation of the other parameters that they did not consider, but they did list. They could also have had more quantitative predictions from their model and some analysis of the flame rather than just the sound. For the opposition, some key insights that they have were that, again, that the qualitative explanation was a little bit lacking. They also encouraged the reporter to explore more aspects of the problem statements and some more exploration of the theory and experimental discrepancies. And also they again brought up the key parameters. So some things that they did well, I think they pointed out a lot of areas of improvement well, and some more suggestions to improve the theoretical model while making it analyze quantitative data. Some next steps that they could have explored would be to suggest some more possible changes in the qualitative as well as the quantitative theory for improvement, as well as going more in depth into the topics that they questioned about, rather than exploring a wider variety. And finally, a little bit more about how they would incorporate the collimation that they mentioned into their presentation. So for the discussion, the first topic brought up was the frequency response of the speaker. The opponent mentioned that there were differences in efficiency and recommended using a proper decibel meter rather than an app. The reporter responded by saying that they accounted for the characteristics when purchasing the speaker. I think that it was commendable that the speaker was checked for its good response, but that the impedance was not necessarily correlated with efficiency, i.e. that not all the electrical energy that you put in would be converted into sound energy, and so you still have to characterize the heat loss that occur at different frequencies. The next topic was the type of waves. The opponent asked whether they investigated both standing waves and traveling waves. The reporter responded that they only investigated traveling waves. I agree with the reporter because the standing wave would result in constant areas of high pressure and low pressure, which would not be very interesting to investigate because that would just lead to the same results as if you just measured a totally high pressure or low pressure environment. They also talked about the fuel source. So whether the burning output of the candle is constant. The reporter responded by saying that the wick was cut to keep it constant. And we agree that it's constant because the evaporation rate is proportional to the surface area, which is obviously constant, but that other fuels would still need to be explored since they had different burn temperatures and ignition temperatures. They also had a discussion about the experimental data fitting with the curves. The opponent mentioned that the fit curves did not match well with the data and that they were lacking a little bit in data points and error bars, and they suggested performing a fast Fourier transfer of the frequency in order to identify problems with the speaker. The reporter responded by saying that the pressure increases with a log scale of decibels and that they had 3 trials per data point. We agree with the reporter in that the pressure is a log scale, but the empirical data still did not correlate well with the trend line, and there is no explanation of this discrepancy. Also, we believe that for experimental data, it's more important to discuss its comparison with theoretical data rather than it just including a trend line. And finally,
Okay, so now it's a 2 minutes time for the remark of the reporter.
So I guess to summarize it all up, in our discussions, we did talk about further improvement or further ways to improve my experimental procedure, which I do totally agree with you. I guess very smart of you to and suggest me to put FTTs or FFTs or I guess using a real decibel meter or varying I guess fuel types. And I also like the idea where you sort of a sound culminator, which I did allows the sound to be parallel. That was really smart. I guess there was lots of insightful discussion and next step tips we have all discussed about, and I guess it was really valuable, right? Because if I were to do this experiment again, I will follow your tips. Maybe I'll add something that you said to make my experimental data fit better. I also do agree that I didn't go that in depth with discrepancies and I guess the trend line. However, when I was doing my experiment, it was considered, and I did do it. That's why I could present my graphs, right? But yes, a possible next step presentation itself, right? Directly go into the discrepancies way more into detail, as well as as well as the trend line, and focus more on, I guess, comparison of the two. I did do comparison, but I didn't do it that much because I saw well, I don't have to directly speak it. I could just show it, and I guess it should make sense. So I will take those next steps. And if I do have a presentation in the future, I will think of this and try to improve myself better. Thank you.
All right, cool. So now it's the questions of the juror time, and just feel free to start whenever you have a question.
Okay, I guess I can start. Anthony, could you bring up your slides again where you showed your decaying exponential curve?
Oh, of course. Which one do you want to see? Is it
Yes,
this
that one. Yeah. Is there a part, because the decibel being a log scale,
Mhm.
it probably makes some sense to try and test with greater granularity, like 62, 63, 64. Is there a particular reason why you only tested every 10?
I did go every 5. It's just not showing. The scale was kind of messed up. And the reason I did this was I don't think my speaker could be that precise, right? It's after all a home-built speaker out of amplifiers. But it is a good possible next step. If I have better equipment, I will try to go from 70 to like 80, because the decibel meter I was using, it wasn't giving me like concise. The most accurate I could get is every 5 decibel up. It wouldn't be doing 1 decibel up. I don't know why, because it was also a phone app, so I guess that was the reason.
Okay. And more importantly, for your graph on the lower right,
Lower right here.
Yes, you matched it. You put a curve fit of a parabola, but the problem with that is that if we take your word, that means at 75 hertz, you built a time machine. It takes -1 second to extinguish the flame.
Oh no, the parabola is just a line of best fit. It wouldn't. It's not like 100%, right? The R value isn't that high.
Yeah. Right. So I mean, this for the future, when you present data and you say this a line of best fit, the best fit has to have some physical significance. Like
yes.
That means you have to discount using that parabola. If you have to choose a worse fitting line, but still makes physical sense, I think that would be better.
All right. I'll take that. And
yeah.
Thank you.
Any other question from the next jurors?
Yeah, sure. I can jump in and ask a question. Okay, for a quick question for the reporter first, I guess let's more thinking about things. If you just compare like playing your speaker versus blowing on the candle, what would you expect to have more or less of an effect, and why?
I will feel like me blowing on the candle will have more of an effect. And this is due to, well, the speaker only uses pressure waves to generate an airflow, while I'm using a differential pressure to generate airflow, right? My lungs, when I exhale, I believe there's high pressure in my lungs. So when I exhale it, there's greater wind speed from my lungs. I think blowing on the candle will have more effect. And also the high wind speed also could attribute to a greater rate of equalization of the air temperature with the flame temperature, which just kills all 3 legs of the fire triangle: fuel dispersion, heat, and oxidizer, because it will also disrupt airflow. Because we have a convection of the candle, and by blowing on it, first of all, we're disrupting the convection, and second of all, using a sine wave, we could approximate the peaks and troughs as a defined amount of time. So therefore, at one defined amount of time for the troughs, it might cut off the necessary limiting moles. Like let's say the candle needs, let's say, 3 moles of oxygen, but at a trough of the sine wave, it could cut off that 3 moles and turn it, let's say, into 2 moles, which will just kill combustion. I think that's also
Yeah, awesome. Okay, thank you. Yeah, just to get one question in for the opponent quickly, what parameters of the flame would you like to investigate?
So, so
For the opponent, sorry, yeah. I want to give them a chance to have an answer.
Sorry. So as we mentioned like before in our discussion, we think several key parameters that we could vary. Secondly, like the amount of gas or fuel used. Oh, sorry. Oh, could you hear me?
You cut out for about 3 seconds.
Okay, I'll start again. So I think a few parameters that could be varied are first, like the amount of gas or fuel. Secondly, like the different types of gas. Thirdly, like the size of the flame. I mean, this could be very hard to control, but it's important to the experiment to see like how sound affects like the flame extinction, I think. Yeah, those are several.
Okay, thank you.
Sorry, while there's like a few seconds left, I'd also like to add like the temperature of the flame would be interesting to analyze.
Okay, cool. So that's time's up, and that wrapped up our first round for the physics match. And all right, so now the jurors, please like sign up all your score sheets and then upload that to a link I just sent in our Discord channel. So since for the finals we are not revealing our score, so you can just upload that and then let me know when you finish uploading.
Yeah, I'm done.
Good. Okay.
Mhm.
So when you're done, just let me know, and we will move on to the next stage around like 5 p.m.
Mhm. Just as a side note to the opponent who did that last minute addition of investigating the temperature, you'll learn this later on when if you study combustion in undergrad. The flame temperature is primarily a function of the fuel you're using. So when earlier you said, I want to try changing the fuel, that also already changes the flame temperature.
All right. Yeah, thank you so much for like the clarification.
Are you done?
I'm done uploading the scores.
Great. Thank you all. So just one more minute, and then we can move on to stage 2. And in stage 2, the opponent in round 2, the reporters will be Schrodinger's cat girls, the reviewer will be Shrimski's, and the opponents will be Maxwell's demons. Just be ready for those 3 teams. And by the way, just a reminder, in case you guys didn't see my Discord message, is that you must ensure that in each of the rounds, the students you put on must be different. Okay. All right, I guess we're good to start. So now it's a 5 minutes preparation of the reporter, which is Schrodinger's cat girls. And who's gonna be presenting, by the way?
Daniel.
Daniel. All right, good. Okay. So just let me know when you're ready. We can start the clock.
Okay, I think I'm ready. Before the time starts, can I just double check I'm audible and visible to everyone?
Yes, I can hear you and I can see you well.
Great. So my
Perfect.
time will start in 3, 2, 1. Good morning, everyone. I am Daniel Cui from Team Schrodinger's Cat Girls, and today I'll be presenting Problem G, Ruler Cannon. So the problem statement read, two rulers are tightly held together against each other. A round projectile, such as a plastic bottle cap or a ball, is inserted between them close to one of their ends. When an extra force is exerted on the surface of the ruler, the projectile is ejected at a high speed. Investigate this effect and the parameters that affect ejection speed. The parameters we'll be considering in this experiment are the magnitude of the applied force, the location of the force applied, and the Young's modulus of the ruler. Here's an overview of our presentation. First, we'll be going to our experimental setup. So this is our overall setup. Our experimental setup includes a linear actuator connected to a DC power supply. One end of the rulers are clamped and the other end are free. The linear actuator applies a force a set distance away from the clamped end, and a fixed block is placed on the other end to apply an equal and opposite normal force to the other ruler. In this experiment, some measurement methods include a digital caliper to measure small deflections, a mass balance to measure mass, and metal rulers to measure length. Here are the materials we use to conduct these experiments, which include two metal rulers, both metal and plastic. Two rulers, both metal and plastic, with similar dimensions but different mass and Young's modulus. We also use a ping pong ball as our projectile. Now let's characterize the Young's modulus of the metal and plastic ruler. Young's modulus, or E, is a measure of the material's resistance to elastic deformation under tension. This equation is given by E equals FL cubed over 48 I delta. Here, F is the applied force, L is the length, delta is the deflection, and I is the second moment of area given by the equation I equals BD cubed over 12. Experimentally, we can determine the Young's modulus by clamping the rulers on either end of the table and measuring its vertical deflection under different applied forces. Here, I tied a string to the middle of the ruler and hang different masses off it. The applied force is equal to mg. As you can see, under tension, this ruler will deflect vertically. So thus, we can measure this deflection by taking videos and photos of and measuring the deflected distance in tracker. Here is a picture of our actual experimental setup. You can see the metal ruler, clamps, hanging mass, and a metal meter stick for reference. By plotting the mass versus deflection, we can find the slope of the fit line equal to GL cubed over 48 IE. Given that all other variables are constants, we find the Young's modulus of the metal ruler to be around 101 gigapascal, and that of the plastic ruler to be around 2.98 gigapascal. So next, let's characterize the force of the linear actuator at different voltages. The maximum voltage my linear actuator can operate under is 12 volts. However, the magnitude of the force exerted varies based on voltage. Therefore, I tested the maximum mass the linear actuator can lift at constant velocity. Thus, we're able to determine the force of the linear actuator to be Fa equals mg. By plotting this over voltage, we can determine a roughly linear relationship of F equals 0.88 V plus 0.57. So next, I'll be moving on to my theoretical models. First, I'll be giving a qualitative explanation of this phenomenon. Let's take a look at the geometry of our setup. L is the length of the ruler, big M is the mass of the ruler, small m is the mass of the ball, and R is the radius of the ball. The applied force, P, is applied a set distance away from the clamp end. The ball is tangent to the ruler a set distance B from the clamp end. Theta is the angle between the ruler to the horizontal, with theta equals arctan R over B. An important thing to note is that the system is symmetrical across the horizontal axes. First, let's analyze the forces in the system. As Fa is applied symmetrically on either side, the ball feels two normal forces at the points of tangency. It also feels two forces of friction opposing its direction of motion. And because the ball's is limited to the horizontal axis, we can take the horizontal component of Fn and Ff. Once the horizontal component static friction is overcome, the ball accelerates left and be ejected out. However, this model is limited because first, it assumes the ruler to be a rigid body, which is obviously not true because it's elastic and bendable. Secondly, B and theta are functions of time. That is to say that ball's contact point with the ruler changes as it is ejected, with B increasing and theta decreasing. Thus, this means that normal force and the net force acting on the ball are time dependent, making it difficult to evaluate its ejection velocity. Lastly, it is difficult to experimentally determine the coefficient of static and kinetic friction. Alternatively, you can approach this problem from an energy perspective. By calculating the elastic potential energy with a ruler when deflected, we can use the energy conservation 2 times U elastic times eta equals 1/2 mv squared, where eta is the mechanical energy coefficient. We can rearrange the equation to find V. This approach is better because it handles energy loss due to friction without directly measuring the coefficient of friction, and the model is not time dependent. Next, I'll be moving on to my quantitative theory, the Euler-Bernoulli beam model. So some assumptions of this theory include, 1, we assume the rulers to behave as linear elastic beams. This means that deflections are assumed to be small and the material stress-strain relationship is linear, and shear deformation is negligible. Secondly, we'll assume that an applied force load the beam quasi-statically. Dynamic effects during loading and the detailed time evolution of the snapback are ignored, allowing the use of static deflection formulas. Thirdly, we assume that the rotational kinetic energy of the ball is negligible. Considering the force of friction on either side to be symmetrical, the ball should barely rotate. Therefore, all the elastic potential energy the rulers have constant material properties, and variations in material stiffness or cross-sectional geometry are neglected. So the governing static Euler-Bernoulli beam theory is mx equals IE multiplied by the double derivative of yx with respect to x, where E is the Young's modulus, I is the second moment of inertia, yx is the deflection profile, and mx is the bending moment. Because there are 2 loads acting on the ruler, one from the applied force P and the other from the normal force of the ball, the deflection profile should be a superposition of N and P. Thus, we get the equation yx equals ynx plus ypx. By solving the static previous slide for a cantilever beam with a fixed end, we get the following equations. If anybody's interested in the full derivation, I'm happy to refer to my appendix for more detail, either during the discussion or during the juror questioning period. So here regions, the 2 regions for yp, and also similarly for the 2 regions for yn. Because the differential equations are linear in y, the principle of superposition applies. Thus, this is the overarching equation that will determine the deflection profile of the ruler in this problem. As demonstrated here, it is a piecewise function depending on the location of x. Except there is one problem. Every single variable in this equation is known except for normal force, n. How do we determine the magnitude of the normal force, n? First, if we define phi as the angle from the tangent line at any given point to the horizontal, we find yx equals dy over dx equals tan phi. Or alternatively, phi b equal to arctan of the y prime of b. We can initially guess a value of n and use torque balance along the ruler to find its normal direction. Thus, we can update and calculate the new value of n given the current normal direction, and update the value of n. And therefore, we can iteratively approach the true value of n until it converges. So here we can see our deflection profile equation in action. Given such input parameters, we can actually determine the shape of our ruler. Using the deflection profile we calculated, we can now calculate the elastic potential energy of an Euler-Bernoulli beam as follows. Because our deflection profile is a piecewise function, we split the integral into 3 parts in order to correctly evaluate its potential energy. Using energy conservation, 2 times potential energy times phi equals 1/2 mv squared. Rearranging this equation gives you V equals the square root of 4 times phi times U elastic over m, where phi is mechanical efficiency coefficient. By analyzing the ejection velocities in tracker, we're able to determine the mechanical efficiency of the system to be around 0.8. Now let's look at some key parameter interactions then. Our key parameter, we said that such key parameters, there are 3 key parameters that affect ejection speed. And overall, we found that the magnitude and the location of the applied force has a positive correlation with ejection speed, while the Young's modulus of the ruler has a negative correlation with ejection speed. First, let's try varying the applied force. Given these input parameters, we can observe that the ejection velocity increases linearly with the applied force. At the beginning, we observed small deviations from the theory to experiment because small applied forces, a larger percent of the elastic potential energy turn into rotational kinetic energy, and the ball basically just roll off the platform instead of being ejected out. And because we didn't take rotational kinetic energy into account, this results in a slightly lower ejection velocity as expected because it's less less energy is going into translational kinetic energy. Here is the same graph you can see from the plastic ruler. We see for the plastic ruler, there's a much higher, we still observe the small deviation values for the applied force, but overall we see this a positive correlation. Furthermore, we can observe that the plastic ruler has a much higher ejection speed given the same applied forces compared to the metal ruler, with the plastic ruler reaching 3 meters per second, while the metal ruler only reaching 1.6 meters per second because the plastic ruler is more bendable and has a lower Young's modulus. Secondly, we try varying the applied force location. Given such input parameters, we observe that the ejection velocity increases sort of exponentially as we apply the force closer to the ball. Notice that there is deviation at the beginning of the graph where the ejection velocity is 0. This is because when you apply a force too close to the clamp end, the rulers are too close together, and therefore they hit each other and cannot be deflected further. The resultant elastic potential energy were not able to overcome static friction barrier, and therefore the ball is not ejected out of the ruler. If we do the same thing for the plastic ruler, we observe a similar trend, and we observe similar deviations as well. For overall, we say that increasing applied force location increases the ejection velocity, and also we can observe the plastic ruler also has a higher ejection velocity compared to the metal ruler under similar applied force location parameters. So in conclusion, in solving this problem called ruler cannon, we had a controlled experimental setup, both for our overall setup and also for characterizing many constants necessary in the experiment. For example, the Young's modulus of our metal and plastic ruler, and also the applied force based on voltage of my linear actuator. We had thorough theoretical model analyzing the static Euler-Bernoulli beam theory and energy transfer, and we were able to vary key parameters such as the applied force magnitude, the applied force location, and different Young's modulus of the ball. Overall, we say we did a very good job on this slideshow. Here's my references, and thank you so much for listening.
Thank you, Daniel. Oh, sorry, could I start?
Yes, please.
Go ahead.
Okay, so I just had some questions. I think around at slide 12, you said that B and theta are time dependent. So wouldn't you be able to find them based on position? Wouldn't theta be a function of position as well?
Yes, theta is a function of the position of the ball,
Right.
position of the ball, because theta equals R tan R over B. So B changes over time because the ball goes like it travels within the ruler.
Okay. And you also said it was hard to find the coefficient of friction. So wouldn't it just be really simple? You would just place it on a ramp and then find the acceleration. And then just based on simple Newtonian mechanics, then you would be able to find the coefficient of both static and kinetic friction.
So because our ping pong ball is really light and the ping pong ball is also a sphere, if you put on a ramp, it will roll down really, really fast. We assume that because if you ever felt a ping pong ball, it's probably really smooth. Therefore, its coefficient of friction is probably too negligible for you to accurately determine.
Okay, all right. Thank you. And you also said your beam theory. There was a slide with beam theory, and you had two forces. There was a normal and an applied force, which was what caused the ping pong ball to shoot out. Did you consider the force at the clamped end, or did you just consider it as like a stationary end with slope of 0?
No, we did not consider the force at the clamped end.
All right. I guess having a clamped end model also works for this scenario. So could you go to a slide where you have the variable phi as I think, system efficiency? Right. So
wait, this one or energy conservation?
this one's fine. So for phi, you just matched it up with your graph. Would that be correct?
Yes. So we're able to experiment by calculating the elastic potential and also measuring velocity. We're able to just rearrange the equation to measure phi.
Okay, so it was just total energy versus the energy of what was actually experimentally determined. Yes. Okay, all right, thank you.
Cool. That's the time for the opponent to prepare. The opponents should have the slide to be presented by now. Right. The timer starts now.
All right. So my name is Ethan Wang, and I'll be being the opponent for ruler trick. So two rulers are tightly held against each other. A round projectile is inserted, and when extra force is applied, then the object shoots out. So the task that we assigned for this problem was to construct a reliable experimental setup to reproduce the ejection, to analyze the geometry of the system, to analyze the dynamics of the system, construct beam formulas with a comprehensive model, and analyze relations between parameters. Overall, I think that the presenter did an extremely good job of these, other than the dynamics as well as beam formulas, which I think could be improved upon. So the summary of the report is as follows. There was a theoretical analysis with the qualitative explanation of just simple forces. And then they incorporated their Euler-Bernoulli beam model, which was based on energy and a constant of phi. Their experimental verification was varying applied force location, and varying Young's modulus, which lined up pretty well with their theory. So, sorry, I can't see the timer. Is that okay? I can see it now. So some of the merits that we assigned to their presentation was that they had an extremely good experimental setup with the linear actuator and the blocker. We thought that this was very well thought out, and it deserves merit. And I think their determination of constants, for example, Young's modulus, was very well thought out, and there was an accurate determination, especially when you could see the data points on the graphs. There was a comprehensive theory involving the Euler-Bernoulli beam theories, and even though they were more based on energy than forces, I thought they were well done. There was a good correlation with their graphs, so the applied force location, and Young's modulus. So some possible next steps that we assigned were the abundance of parameters. So there were only 3 parameters they had, which was the applied force, applied force location, and Young's modulus. I think friction could be included, and maybe position of ball and radius of ball. So they also didn't necessarily define variables through position, rather than they mentioned time. So I think that you can have just moments on the beam and then integrate by the Euler-Bernoulli beam theory rather than using energy. So the determination of phi would be considered acceptable, although I think that friction and the coefficient of static friction could be considered, and I hope that this is something that we talk about during our conversations. And as well, just going back to the clamped end model, I think that you could also just integrate all the moments on the beam and then come up with an equation for the beam rather than assuming a clamped end model, although it does still work. And I think that the integration of forces could be a possible next step, as they used a comprehensive formula rather than splitting the forces on the ball separately. And their presentation was more energy dependent, with experimentally finding values such as phi, which I think that friction or the coefficient of friction would be a better representative of the energy loss in the system. So overall, I think that the opponent did a good job. And just going back, I think that their experimental verification was extremely well done, and their theoretical analysis was fairly comprehensive. Okay, thank you.
All right, great. Now it's time for the discussion. So take the stage.
So my first question is that you said that plastic shot the ball out faster than the metal. Would that be correct?
Yes.
So why do you think that would be?
Because plaster has a much, it's more bendable and has a much lower Young's modulus, actually by 2 orders of magnitude. While I'm sharing my slide, I think I can tell it by memory. Hang on. Let me find my slide.
No worries.
So for memory, I think it's plastic is 2 point something. It's like 2 point something gigapascal and 2.58 gigapascal. And for the metal ruler, it's 101 gigapascal. So they're actually all by 2 orders of magnitude.
So would the energy be more like would there be more energy stored in the system when Young's modulus is lower?
Yes.
And could you like show me a formula where that's represented?
Like for example, for y, you can see the Young's modulus in the denominator. So
Right.
as modulus is smaller, obviously, though you're gonna have a larger yx, means that deflects more, which also you can see it's more bendable. And for the overarching thing, you're integrating over y, so the value of y matters.
So what do you think that it's because since it's softer, the theta would increase, and the horizontal component would be sine of theta, and the normal force would be cos of theta. So would you think that it's because it's softer, so the theta increases, so the horizontal component of the force would increase rather than the vertical component or the normal force acting with friction?
Like, are you saying that there's gonna be a larger component of the horizontal component of the normal force gonna be larger when it's more flexible?
Right. So for example, if you have a ruler and you bend it, then this theta would be greater if it's softer. So then the horizontally applied force would be greater because we didn't do it by energy. We did it by forces, and then we integrated those forces over the distance. So then I was just wondering what your thoughts, because I'm sure energy is a valid explanation as to why it's faster, plastic's faster, but then we did it by forces, and we came with the conclusion that because it was softer, the angle is greater, and then the angle causes sine to be greater rather than cos.
Okay, so if you did it by forces, I would actually want to quickly discuss some of the limitations and some of the potential ways you can do with forces, because that's also one of the ways I considered. So you said that you integrated over acceleration.
We integrated over distance.
You integrated over distance, but have you taken into account that the forces acting on the ball is time dependent? As in that at B, your B is dependent on time because the ball is like moving out of the ruler, right? And therefore, because your B is dependent on time, your theta is also dependent on time because our radius is constant and theta equals r tan r over B. And therefore, because theta is dependent on time, the horizontal components of the normal force and the friction is also dependent on time.
Well, why wouldn't it be dependent on distance? Why does it have to be dependent on time? Because we did everything by distance and there was no time value in ours.
Okay, because if you like, I also considered a force perspective, but what I did is I would use Euler's method. So I would find use Euler-Bernoulli beam to find the deflection of the beam at different timestamps. And also you can, after determine the coefficient of static and kinetic friction, you can determine the ball's location and velocity at each timestamp. And you can also use like a while loop to simulate and to check every time whether the ball has exited the ruler. So that's what I would think if I were to approach this problem with the force perspective. I'll probably do it dynamically using Euler's method.
Okay, well we just came up with a beam deflection formula based on the Euler-Bernoulli beam, and then we integrated all the moments, and then we got an equation that had the normal force in it as well as theta. So then we just it's the horizontal minus mu of the normal. And also just another question on mu. So this is what we did. So to find the coefficient of friction of the ping pong ball, we simply just cut the ping pong ball in half and then put a weight in it. So then it would just, you would find the coefficient of the ping pong ball against the ruler rather than doing it by phi. So do you think that phi is an accurate enough representation of the system?
I think first of all, I think phi is pretty accurate considering how well my theory correlates with my data.
Okay, yeah.
But also I think because static and kinetic friction is different, in order to like accurately have an accurate theory with a force model, you need to determine the critical point in the critical value in which the system goes from static friction to kinetic friction. And therefore, that's kind of like, you see, they come in play together in different proportions, and you have to actually evaluate when they turn from static into kinetic, which is pretty hard. So I think using a mechanical efficiency coefficient is better because it generalizes it in like energy loss.
Right, but wouldn't it be right when it overcomes static friction, it would be into kinetic friction?
Yes.
And kinetic and static friction are both like pretty easily determine just experimentally, right?
Mhm. So
So-
what I actually
Right.
what I want to determine when I want to determine the coefficient of friction, I tried the same thing as you. I put a weight on the ping pong ball and so apply a large normal force and I tried to drag it with a force meter. But the problem is I didn't think of cutting it in half, so I just squashed my ping pong ball instead. It's kind of hollow, you see. So it didn't work out. But I was able to determine that the coefficient of friction is really small and
Right.
it's really hard to determine experimentally.
Mhm.
About the other thing you mentioned, though, because you mentioned in the rapid fire questions about whether I consider the force at the clamped end, would you like me to elaborate more right now, or do you want to discuss it later in like a theme?
Sure, go ahead.
Because I know that I didn't have time to put a full derivation of my Euler-Bernoulli beam theory,
Okay.
so I can also refer to my appendix A. Because in my appendix, okay, first of all, let me quickly go through this. So you split the region between like x smaller than A and x larger than A. And smaller than A, you just have your equation for mx, and then you do your first integration and you do your second integration. But as we all know from calculus, when you do integration, you have constants, and therefore you need to apply some boundary conditions in order for you to solve for that constant. Here we impose the boundary condition y prime 0 equals 0 and y 0 equals 0. That is to say that because the ruler is essentially flat at the clamped end, y prime is 0 at that end, and therefore that end actually have 0 force acting on the ruler according to our derivation of the Euler-Bernoulli beam model.
Okay. So, but in reality, would it be a 0?
In reality, I say it would be hard to tell because note that here for my normal force, I was able to determine the normal force from torque balance. Like essentially, imagine you have like, normal torque balance on a rigid body, right? Here we just found yx and we found the normal direction at
Okay.
x.
Okay.
You can still do a torque balance on a on an elastic body.
Okay.
Just doing vector directions. And because I only consider two forces, the normal force is the resultant of the fact that I only consider two forces acting in my system.
Okay, I guess just based on the energy, like I guess it makes sense just based on the two forces.
I'd like to emphasize that I think my theory, like considering the two forces, is enough because it correlates well with my data. So I don't think an additional necessary force would be necessary, but it would be fun to investigate.
All right. And another question I had is, I think this kind of ties in with the plastic ruler being faster than the metal ruler. It's just the role of the theta. So, sorry, just while we're on the slide, on the plastic ruler, do you think the little notches in the ruler had any effect on the ejection speed?
I don't think so. Because when we measured Young's modulus, we measured the Young's modulus of this ruler with holes in it. So I think Young's modulus.
But I get that. It wasn't about Young's, like my question's not about Young's modulus. So when the ball goes across the ruler, do you think that there would be a normal force in the opposing the direction of the ping pong ball? Just based on the notches in the
no, it's too small for it to have any effect on the ping pong ball. The ping pong ball is much larger.
Okay, all right. Another question, well, before I brought up this question, did you notice that there was a sweet spot for where the force was applied? So for us, if we applied the force, so if this was a ruler and the ping pong ball was here, if we applied a force right before the ping pong ball, there would be a great force, but the theta would not be enough to overcome the friction. And if we applied it too far back, then there would be a great angle. However, the force was not enough. So did you notice that there was a sweet spot for where the force was applied?
No, we do not. We do not find a sweet spot. So our trend is strictly exponential, or actually looks exponential. I'm not sure if it actually is, considering my n was found iteratively. But I think it's an exponential trend. So the closer you are to the ball, the faster it is to eject. If you just do it too close to the ball, it's the fastest thing to get at, like fast ejection speed.
So the closer, like even if it's like a millimeter away, that would be the fastest.
Yes.
All right.
We actually didn't test a millimeter away because you see the the applied force location, because my lead actuator also have a width, it's not infinitely thin. I can only test intervals.
Okay. So just based on your theory, it would be the closest. It would be the fastest if it was closest. Sorry for the time. Thank you.
All right. So now it's a 1 minute time for, sorry, 1 second. All right, so it's now the opponent summarizing the discussion.
I think that was a very fruitful discussion, and I think that we had multiple points in agreement, even though we had different models. So Daniel had an energy model, and I had a force model. Although I think he had an empirical value of phi, and I determined the frictional constant. I think most of our opinions agreed and matched up. However, I think that integrating by forces would still be the better way of doing this problem. Although the agreement between his theory and his graphs are excellent. And I think that overall was a very fruitful discussion, and it opened my eyes up to what the energy dynamics are of this system. And I think that's something worthy of pursuing further during maybe the next couple of months. Thank you.
All right, great. So now we go move on to the next stage, which is the reviewer. So you may begin, reviewer. Hello, Shrewsky.
Turn on your camera too.
Hi, I have a question for the reporter. Can you go to slide 12?
Yep. You can ask your question while I go to the slide 12.
Do you have an image of your force characterization setup?
Hang on. Hang on.
Yeah.
No, because I borrowed items from the physics lab and I forgot to take a picture. So I only realized it after I returned the items, like the hang masses. So I wasn't able to get a photo in time. But here is a diagram representing what I actually did.
Okay. I recommend using a spring or a scale, as the range of the linear actuator is actually limited. I have a question for the opposition. Do you believe that using a ramp to characterize, would it work?
It worked pretty well for me, right?
Do you think there are any issues with this?
With using a ramp?
Yeah.
Maybe the error based on the angle of the ramp? That would be the only one that I would be able to think
As
of.
in use the ruler as your ramp?
I did use the rule as my ramp. However, I did support the middle with like a book, so then it wouldn't deflect during the experimentals.
Can you go to your for the reporter, can you go to your experimental setup?
Yep.
Did you control the angle of the force?
It was always perpendicular.
Perpendicular. It looks like it's only perpendicular to the ruler at the start.
It's perpendicular. It's perpendicular to the ruler at the initial position.
Is it perpendicular while it's compressed?
Not really, but its effect is negligible. Because the ruler, the y-axis, the deflection profile of the ruler will change as it is compressed because as we apply a force.
Okay, we disagree, but we can move on. Do you think using the Euler-Bernoulli is valid for the displacement, considering you used a plastic ruler?
What do you mean? Could you repeat that question?
Do you believe using the Euler-Bernoulli is valid for this, this magnitude of displacement?
Yes. Because our data actually reflected the theory, so we think it's a accurate way to model the plastic ruler.
But you used a fitting parameter, so you don't know.
So if I don't use a fitting parameter, are you saying that I should assume 100% energy transfer?
No.
Yes, because there's energy loss due to friction, and therefore I need to account for the energy loss due to friction within my system.
We found that Euler-Bernoulli only works for small displacements, so maybe using von Karman equations would better account for larger deflections because you used a plastic ruler.
Okay. Thank you so much for that suggestion.
For opposite.
Sorry, it's time's up. All right. So now it's the preparation time for the reviewer. All right, the reviewer should get the slides put on by now. All right, the reviewer. All right, start the timer, Daniel.
Am I audible?
Yes, you may start. The timer has started.
Okay. Hi, my name is Jessica, and today I'll be reviewing problem G, ruler cannon. So there are 4 tasks we identified. Firstly, to qualitatively explain the phenomenon. We believe that the report did a good job of this. Task 2, to quantitatively model the phenomenon. We believe that this was there could be more work to this. For task 3, to control the relevant parameters in a reproducible experimental setup, we believe that it was well done. And for 4, to explore various key parameter interactions, we believe that this could be improved. So summary of the report. For the theoretical analysis, the reporter first did a qualitative rigid body analysis, did energy modeling, and then moved on to Euler-Bernoulli beam theory. And for their experimental confirmation, they talked about efficiency constant fit, varied their applied force, and then went into Young's modulus. So for the reporter, I think they had a good experimental setup. It was reproducible. There was a good qualitative explanation and a good use of beam theory to account for bending. There was also good fit for the theory experimental comparison, and they used the fit constant. For possible next steps, I think they could account for larger deflections in their Euler-Bernoulli theory. For their fit efficiency constant, we'd prefer if you characterized or modeled relevant losses such as friction or sound, and it should not be constant. They could explore more parameters such as ball material, ball radius, and mass, and they could use a dynamic kinematic beam model because it's like more insightful than energy, we believe. A summary of the opposition. The opponent recommended three key insights. Firstly, they recommended the Euler-Bernoulli force model. Secondly, using forces or energy as a method. And then thirdly, considering coefficient of friction. We believe that they did a good job bringing up the fit efficiency constant as an issue, but I think they could better suggest, they could suggest a better alternative. They also brought up using forces instead of energy. We believe they could define benefits or limitations over energy, and also we don't really understand what they mean by integrating over distance. Possible next steps. They brought up some irrelevant points such as a boundary condition on the end because it's a standard practice. They could bring up more questions in rapid fire, and for their force model, they didn't realize small deformation of issue of Euler-Bernoulli, and they seemed a bit confused. So firstly, for the discussion, the first point raised, why does plastic shoot the ball out faster than a metal ruler? When it's softer, theta would increase, so larger component of normal or horizontal force. The reporter's response, the plastic has a bigger Young's modulus by 2 orders of magnitude, and there'd be more energy stored in the system when there's lower Young's modulus. We agree with the reporter, changing Young's modulus increases deflection. Secondly, they talked about integrating force over distance with Euler-Bernoulli, and the reporter talked about limitations of the force model. We agree with both. We believe that force is more insightful. However, the opponent seems confused, and we believe that we should be integrating over time. So we agree with the reporter there. Thirdly, they bring up finding coefficient of friction, how it's easy to find by putting a ball on the ramp. And the reporter's response is that it turns into kinetic friction. We agree with the
time's up.
Opponent.
Yeah. So let's move on to the next one. So now it's the remarks of the reporter. 2 minutes. Take your time.
Great. So thank you so much for that amazing presentation from both the opponent and the reviewer. I'll just first quickly summarize my presentation. In my presentation, I had a good experimental setup using linear actuator connected to DC power supply, and I also used different rulers with different Young's modulus, and I characterize what constants such as the Young's modulus of the ruler, the force of my linear actuator. I also had a thorough theoretical model using Euler-Bernoulli beam theory and energy transfer. And lastly, I varied key parameters such as the applied force magnitude, the applied force location, and the Young's modulus of the ball. So I have to quickly address some of the themes that came up during our discussion. First, we had a debate around the force versus the energy model. The opponents said they use a force model and integrate over distance, while I use an energy method and use energy transfer. I believe doing a force model is definitely feasible. However, if I were to do it, I'll use Euler's method to simulate time step and calculate distance and velocity based on the integration of net force and integrate time instead of integrating distance, and that's what we disagreed upon. Secondly, the opponents gave me a good suggestion on how to determine the coefficient of friction, which I thank Ethan for. And lastly, regarding the extra parameters I could investigate, which was both brought up by the opponent and the reviewer, such as both ball's material, ball's radius, and mass. I would say that it's not feasible for me to vary these parameters because in order to vary parameters, you have to keep all of the other variables constant. However, we're not able to find balls that differ in mass but have the same radius and material, and we're not able to have balls that had different materials and but have the same mass and radius. So we believe that's a material limitation for us that we couldn't explore further. And overall, I think it's a very fruitful discussion from both the opponent and also very good questions asked by the reviewer. And I thank everybody for attending this physics match. And thank you so much, everyone.
All right, cool. We move on to the next stage, which is question of the jurors. So feel free to ask the questions now. Anyone wants to start?
Okay, I can start. Daniel, could you please show your slides again, showing the Young's modulus of plastic? So you found that the Young's modulus of plastic is 2 orders of magnitude smaller than metal?
Yes.
So that means the metal rulers are, of course, stiffer, meaning they are harder. You have to apply more force just to bend them a little bit, right?
Sorry. Yes, they're stiffer.
Yes, they're stiffer. Now, when you built your catapult, were you able to push the ping pong ball the same distance inwards for both the plastic and the metal ones?
What do you mean?
So, okay, if this is your catapult, were you able to push the ball all the way in for the metal one? Because it's very hard to bend the metal one, right?
But it's very hard to bend the metal one. But note that essentially without putting the linear actuator and blocker first, without having those two in the thing first, they're essentially just 2 beams clamped together. So I was able to essentially they pretty much could pivot because I clamped them just a little bit. So I was generally able to push them into the same location. Also, the ball has some amount of static friction, so they usually stay in the same.
You have an image, because I can see right now it's plastic rulers. Do you have an image of one where you did it with the metal rulers? In catapult mode.
I'm sorry.
Okay, do you have the data for the metal rulers?
Yes, I do. For the applied force location, yes.
So for the
oh wait, sorry, that's applied force location. I don't have the data for the ball location. I was only able to vary the applied force, not the location of the ball.
Okay. So this is for the metal ruler. Could you scroll down? The next graph below this is for the plastic ruler.
Yes, this is plastic.
So the highest it went was 3 meters per second for plastic. Could you go up to the metal again?
Yes.
At 1.6, and you applied the same amount of force for both applied force.
This is applied force. So it's one of my variable. It's the x-axis. So I changed applied force both.
Okay, so what's the highest applied force that you put for your metal ruler? Around 10
around 11 newtons.
Okay, and can you go to the plastic?
11 newtons.
So around 11.
Yes, because applied force from the linear actuator only depends on voltage. As
okay.
Okay.
All right. Okay. So this is why it looks like okay.
It's only dependent on the voltage. Here in this, let's see in this graph.
Yeah. Do any of the jurors have any other questions?
And also because I have an appendix, if any jurors is interested in the full derivation of the Euler-Bernoulli beam, I can also go through them. but if not, you can ask me other questions.
Now the jurors have any questions you want to ask?
Yeah, I can ask a question if there are no other jurors who want to ask a
Yeah,
question.
sure, go
but-
for it.
Okay, just really zooming out, in the extreme cases, what would happen if, let's say, the ball does not move and you keep pressing with the actuator? What are the possibilities?
So you're saying that there's some cases in which we have zero initial velocity, and why that is the case? There's zero ejection velocity?
What happens if you have zero ejection velocity throughout the whole curve?
Throughout the whole curve, I'm not sure what you mean there, but I have
Imagine an extreme scenario where the ball is glued to the ruler. What would happen?
If the ball is glued to the ruler, I don't think he would move.
Okay. And so then what would happen?
So the ruler, if it's for a plastic ruler which has a lower Young's modulus, we say the rulers would just hit together, like they would just like hit together, then be no longer be able to deflect more because they're just like together, right? And then for like if you have a higher Young's modulus, or if you apply a lower applied force, then it wouldn't able to have so much of a deflection for the rulers to hit together, but it would still kind of like be roughly together without the ball being able to move.
Great, thanks.
Sorry for the rough illustration. I don't have like very good animations if you just ask me a question on this dot. That's okay. Hopefully.
Yeah.
Any other juror questions? Or
I guess our time's up for this session. So now, okay, so now the jurors, please upload that your files to the Google Drives, and just let me know when you guys are done.
I am done uploading. Also, just as a side note, the derivation of Euler-Bernoulli is on Wikipedia, so I don't know why you have to put it in your appendix.
I mean, that's fair, but like unless like if somebody wants to know, I'm able to explain them with using like graphics. I didn't have time to put in my slideshow though. I was already speaking really fast, and I think I covered all the materials I can without being able to cover the full derivation. Thank you for that suggestion though.
I'm done uploading.
So am I.
Thank you all. Okay, just let me refresh. So in the first, I received 7 score sheets in the first round. So we're still missing 2 right now. Just a second. Oh, so I just need 1 more score sheet and then we're good to go. Wait, what? Huh? Sorry, just 1 minute. I'll just confirm this and then we're good to fly. I think I still need one more from Taha. And then we got the 16 we have for the first 2 rounds.
Yeah, I'm trying to upload. I'm just having trouble putting it on.
No
Just one
worries.
sec.
Take your time, take your time. We'll start in 2 or 3 minutes. So take a very short break and then we can get. And by the way, for the next rounds, the presenter will be, which is our last round, will be Shroomskis. The reviewer will be Maxwell's Demons, and the oppositions will be Schrodinger's Kakarot. And the problem will be magnetic assist. So good. All right, I've received the marks and now we should proceed. So Shroomski, all right, great. You guys got it ready. Okay, so let me know when you guys are ready to present, and Daniel, you may start when they are.
Sure. Let me just check if the screen.
Cool.
You have like a giant rectangle.
That's from Zoom, I think.
It's from Zoom. Oh yeah, that is from Zoom.
Yeah, so just like let it disappear.
Okay, one sec. We'll see if we can change this somehow.
Wow.
Cool.
Sorry, some technical difficulties.
That's all right. You have still have 5 minutes to prepare. While you're fixing, it's just resulting in more dark blocks appearing on the screen.
Yeah, I think Zoom is amazing. Guys,
I think if you select a different share screen, you should be able to fix this issue.
sure. I'll just try sharing my entire screen maybe, and then we'll see if this works. Guys.
I still see the lovely black blocks.
Maybe we live with the black box. It's quite lovely. Like it adds to the presentation flavor, I think. So
The raid block needs to have a
I don't think it really matters as long as it doesn't interrupt or block anything important. So if you feel like it's okay, you can start.
well, if like the opponent and the reviewer are prepared, we can start, I suppose.
Yeah, don't worry about me. You can just start. You're the reporter.
Yeah, if they do first, that's good for me, I suppose. Okay.
Let's go, my goat.
All right, sure. So we can start the timer now. I'm Louis from Team Shroomskis, and I'm presenting problem H, magnetic assist. So the problem statement reads as such. Attach one or two magnets to a non-magnetic and non-conductive base such that they attract a magnet suspended from a string. Investigate how the motion of the moving magnet depends on relevant parameters. So some of the relevant parameters we've identified are the magnet positions as well as the magnet strengths. And for the pendulum length and the mass of the pendulum blob, and the height above the magnet that the pendulum lies. For the pendulum motion, we're investigating the damping, the frequency of the motion, as well as the chaos and end state, so the basins of attraction and predictable patterns inside of this motion. Let's start with an introduction to the problem. So here you can see the problem. So the pendulum going over two magnets. There's two magnets on the base and one pendulum on the magnet. So you can see an interesting chaotic pattern forming. And what happens is that it's attracted to those magnets on the base. So why is this? So when you have a magnet that's hovering over another magnet and they're in an attracting orientation, what you see is that the magnet on the pendulum will experience firstly a magnetic torque that tries to align that magnet with the exterior B field, as well as a magnetic force that pulls it towards the magnet on the base. This is called the Lorentz force. So to model this magnet interaction, which is crucial to our theory, we use the surface currents model, which states that you can approximate the magnet to being a bound. So there's a ring of currents on the side of the magnet, and we can calculate the surface current just through this identity on the bottom over there. So with this model, we can then simulate the magnetic field of the pendulum on the bases using the Ballast-Savart equation. So we do this by integrating across each of those current loops. So one integral for going around the current loop and one for going from the bottom of the magnet to the top of the magnet. And we integrate the B field using the superposition principle. So you can see here our integrated B field. So that shows the B field of the magnet. And we do this using Python number and NumPy to compile the Python code for near compiled performance. And you can see here our accuracy target is roughly in a solution time of less than 50 microseconds. So to compare this to a dipole model, which is a more traditional solution to a problem like this, we can see that the current cylinder is far more accurate at closer distances to the magnet. This is because the dipole model asymptotes as you get closer to the magnet, since it's an infinitesimally small point. So now that we've solved for the B field, we need to solve for the Lorentz force acting on the pendulum that's acting on the pendulum. So once again, we just integrate across these current loops, and that gives us this plot over here, which you once again solve with Python. So what we notice here is that, interestingly, not all of the force is directed towards the magnet on the base. And this is not what's supposed to happen. So the issue here is that we're not taking into account rotation that's caused by the magnetic dipole moment that we discussed earlier. So to take this into account, we apply Roche-Guez transformation to the pendulum magnet. So this is just a vector transformation, and we align the dipole moment of the pendulum magnet with the B field of the magnet on the base. This in turn produces this graph, which is much more in line with what we experimentally expect the force's direction to be. So in this case, you see all of the force pointing towards the magnet on the base. So now that we've solved for the magnet interaction, we can look into equations of motion of the system. So in this case, we decide to use spherical coordinates because we can keep r constant, and therefore we limit 1 degree of motion, and we're left with 2. Once we do that, we can define phi and theta as such, and solve for a basic equation of motion using the Euler-Lagrange equation. Next, we account for external forces. So first the gravitational force, then the magnetic force, which I will expand on in the appendix, just like Daniel, I suppose, and as well as dissipative forces, which point in the direction opposite to the direction that the pendulum is moving. After that, we numerically integrate this using an 8-9 order Runge-Kutta-Fellberg method, which is a derivative of the Runge-Kutta method. So for our experimental, we use a top camera on top of the pendulum, which sits on top of the magnets on the base. So the benefits of this is that we only need one camera to track the 3D position of the pendulum. So here you can see our actual experimental setup. We have a DSLR camera on the top, as well as a ring light directly at the lens for lighting. And we pass this through USB and pass it to OpenCV for processing. So how do we process this? So we use quite a few computer vision tricks to get an accurate reading of the pendulum. And so first of all, we use a large aperture. So the reason we use a DSLR is because the aperture can go to f/1.4, which means that we remove the suspension from the image. Next, we clean the background by using a white paper, and we use an observer point light source, so the ring light at the lens, to remove any shadows in the image. After this, we apply an edge detection algorithm, and then average the high contrast pixels in the image to find the position of the pendulum. So once we have the pixel position of the pendulum, it's quite simple to find the 3D position simply by using a trigonometric transform of the pixel position, which is here. And to calibrate this to make sure this is accurate, we use a ruler, and we just check the experimental data points against what our computer vision says it should be. And you can see there that there's a very accurate camera tracking here. Next, to characterize the important parts of our system, we characterize the magnet using the mobile free axial Hall effect sensor, which we find the B field of the magnet at given distances away. And then we fit our magnet moment using least squares regression. Next, we fit the damping of our pendulum. We find the magnetic dipole moment to be 0.987 ampere meter squared. And next, we fit the damping. So here we fit the damping by fitting the Coulomb friction and the laminar flow friction, as well as turbulent friction, to our experimental data, as well as we fit our eddy current for when we have a magnet. So here we find that our fitted has roughly RMSC of 0.03, which means that's accurately solving for our pendulum. All right, now we can get to the interesting part, which is the regimes of the system. So in this presentation, I'll be going over the two regimes stated by the problem statement. So firstly, we have the single magnet regime, where there's a single magnet on the base. And for this, we'll be analyzing the frequency of the system in relation to various parameters. And next, we'll be analyzing the double magnet regime. So this regime is far more chaotic, which I'll get into later. So first, with the single magnet regime. So here you can see the single magnet regime. This is experimental data. I'm animating this after getting the coordinate. And you can see the motion. So I've cut out the large portions for brevity, but we'll get into those later. So what you see is that first you have this oscillation phase, where it acts as a simple pendulum. The frequency of the oscillation stays constant as it orbits it in a circular orbit. After that, we have an interphase where the frequency that's oscillating at rises sharply. And lastly, you have a trembling phase where the frequency stays roughly constant. So for the simple pendulum phase, as I mentioned, it just looks like this, a normal pendulum oscillation. For the interphase, you see that the frequency increases across time as the amplitude grows smaller. And for the trembling phase, you see that the frequency stays constant while the amplitude is very small. So how do we explain this? So for a simple pendulum, the magnetic force is quite small because magnetic force scales with 1 over r to the power of 4. So in this case, magnetic force is basically negligible, and it acts as just a simple pendulum or oscillating around the magnet. Next, in the interface motion, as it gets closer, so as theta decreases, the magnetic force sharply increases, causing the effective centripetal force acting on the system to increase, thus increasing the frequency of oscillation. Lastly, at the tremble motion, the magnetic force asymptotes because there's a height above the other magnet, and therefore the centripetal force also asymptotes. And this is why the frequency plateaus at a given point. So here you can see the frequency theoretical comparison between our simulation and our experimental data. And you can see a very strong fit between the amplitude versus time. So here's an RMSE of 0.023. Next, for comparing the time versus frequency. So this is what we were talking about before, the different frequency phases of this motion. You can see that our theoretical also matches very closely with our experimental and also exhibits the same modes of motion. So unfortunately, we can only have one data point for magnet strength because when we stack more magnets on top of each other, the mass of the magnets also changes. So we can't keep one variable independent of the other, but we do see that this fits very closely with our theory line, our single data point. Meanwhile, there's also a lot of other cases in this single magnet. So we can get increasingly eccentric from our circular motion. We can go to elliptical motion, or we can investigate linear motion. However, these aren't very interesting, and they all exhibit similar modes of motion that we explored previously. So we'll instead move to the much more interesting double magnet regime. So in the double magnet regime, you can see here that the magnet on the pendulum exhibits a very chaotic motion pattern. So because of this, it's very hard to quantitatively analyze it as with the single magnet case. So instead, what we do is that we use fractal basins. So how do you read this chart on the right here? So each pixel in this chart represents the initial position of the pendulum, and the color represents the final stable position of the pendulum. So blue represents it settling on the right pendulum, while green represents a given pixel settling on the left magnet. And this is actually a gradient of color. So we just take the x position of the pendulum and create the plot that way. So firstly, you can see a time evolution of the basin as we integrate the ordinary differential equation across time. So what we see here is that some key insights are that the ripples are caused by oscillations of the swinging magnet. So this is a trembling motion that's also present in the single magnet case. And it takes roughly 8 seconds to stabilize from the highest initial energies, which occur at the very edges of the plots. Next, for the basin zones, so this is a very interesting phenomenon that we see in the fractal basin. So essentially, you see that there's these basin zones, so big patches of pure green or pure blue. So what these represent is a common path that the pendulum takes towards that end position. So you can see here on this small basin zone in almost the central upper right, so the red square over there. And we see that this is a path of a single pixel in that basin zone. And if we move that basin zone upwards, we see that the path that the pendulum takes to get to its final position stays roughly constant. So it shares a similar path. This is a really interesting observation that we make about the magnetic fractal basin. Next, we see first that it's actually stable in this blue region. So that's the basin zone that we talked about. But as soon as it leaves that region, it exhibits very chaotic behavior. So it goes between the left and right magnet at very fast intervals, and we can't predict that without this fractal basin. So it's chaotic motion. Now for some varying key parameters, we can first adjust pendulum length. So what we observe is that as we increase the pendulum length, the stable zone decreases. Then as we increase magnetic strength, we see that the stable zone increases. This makes sense because the attraction of the magnets increases the stable zone. It's pulling the pendulum towards it stronger. So therefore the stable zone increases. Next, when we adjust the magnet position, so as we move them apart, we observe that the fractal basin shifts in very unexpected ways. Especially at the end, we see that there's an emergence of a third color, which in this case is turquoise. So why does this happen? Essentially, we can explain this using potential hills. So as you move the two magnets apart, eventually a third dip in the potential hill of these in the system appears. And this is gravity. So gravity appears as a third emergent attractor, and this causes the blue in the graph. So in conclusion, I've theoretically modeled the phenomenon. I've created an experimental setup to camera track the pendulum in 3D space, and I've analyzed both regimes of motion of the problem. Here are my references, and thank you for listening.
Fantastic. Okay, so now let's move on to the next stage for the opponent's rapid fire questioning stage. So the opponents.
Hello. Okay. Time begins in 3, 2, 1. First off, Luyu, can I ask you how do you model the rotation of the magnet? Because you assume in your graph, you assume when you orient the rotation of the magnet towards the magnet on the base, you get that magnetic force. But yeah, obviously in two magnet model, it's going to be different, right? Because it's not always going to be aligned to both directions.
Well, yes, there's a superposition. So the B field is formed by the combined B field of both magnets, right?
Yeah.
So the B field, we can find the B field at any given point. And the orientation of the magnet, we make the assumption that's always aligned.
Right. We'll talk more about this later. Can I ask you, there's do you have any experimental verification for the two magnet model? Because you obviously have a lot of interesting theoretical models.
Yeah, you're very okay. Yeah, very enthusiastic. So the issue of experimental verification for this is that's very chaotic, right? So you can't put a point.
In the basin, do you have any experimental data?
Yes, we qualitatively observe the same basins.
Oh, okay. So okay. Can I ask? You model your pendulum as like simple point mass pendulum, right? When you obviously the string it takes the magnet on the pendulum takes time to rotate. So do you assume that it's always instantaneously aligned with the B field?
All right, sure. So if you look at this video here, so it's obviously not going to be aligned when it's outside of the range of the B field. But the thing is that the magnet orientation only really matters when it's in the strong B field, right?
Yeah.
The only effect of the magnet orientation is which direction the Lorentz force is pointing in.
Yeah, absolutely. Okay,
and
great.
the Lorentz force is only important when there's a strong B field. So
yeah, okay. Can I ask, do you have any experimental error, or do you account for any experimental error in the setup?
Experimental errors. So we see that I'm not sure exactly what you're talking about, but we see that our camera tracking is very accurate. So there's not much error there, at least.
Okay.
Otherwise, like sure.
Okay. Great. I think that's time.
Sure.
Thanks so much.
All right, great. So now it's time for the preparation of the opponent. Take your time. Twenty seconds left. The opponent should get the slides ready and start sharing the screen. All right, you may start. And Daniel, you can start the timer.
Magnetic assist. So problem statement as Lou said above. I'm just going to go over this. I think a few tasks that need to be done here are create a reliable and accurate experimental setup. I applaud Liu for doing this very well. Qualitatively explain the phenomenon of chaotic motion, including the forces involved. Again, Liu does this very well. quantitatively model the endpoints and the trajectory of the pendulum. Good. I would like to see a little bit more understanding of the chaotic motion, the two magnet system, which I'm sure we'll discuss later on. And investigate key parameters that affect the pendulum's motion, which is very well done. And finally, explain how results compare with existing principles and why they might differ, which obviously might have not been done as well due to time constraints. Summary report. I think again, Lou had an excellent presentation here. Truly, he had an excellent quantitative model to describe the motion of the magnets with very reliable, like very strong theoretical setup and computational theory. He had a very consistent experimental setup with the pendulum, and it experimentally verifies at least one magnet case and qualitatively measured the basin case for two magnets. I think there's some merits and next steps that we want to look at. First off, again, Liu did a great job characterizing the cylindrical model of the magnet, not dipole here, sorry for a typo. He did a very good job of characterizing the fricative forces, though I would like to ask some clarification questions on that later. He had a very well-made experimental setup and detailed quantitative model for both theory and computational, and thoroughly explained some of the parameters involved, though I do want to ask about the increasing in the pendulum mass as well as magnet strength. There is a bit of a lacking in experimental verification for the basins. I would especially love to see where the border of the basins differ experimentally to theoretically. I would also like to consider the effect of torque over time on the pendulum magnet, because unlike Liu, I don't think the magnet snaps instantaneously, which can obviously, again, because it's a chaotic system, impact the trajectory. And finally, I would like to see Liu model chaos in particular and look into the chaotic motion of that, because I think it's a very interesting part of the problem, though he does do a good job of this with the fractal basins. I want to discuss about Lyapunov exponents later on. And finally, consider additional fricative forces of the experimental setup, because obviously there are some constraints with an experimental, just like in the real world. So yeah, that is my presentation period. I think I would love to move on to discussion with you now.
Sure, absolutely. Let's just start discussion right away. So
Yeah.
do you want to stay on this slide, or should I just go directly to mine?
I think we can just go directly to yours. I'll stop sharing. Can I first ask, do you have any characterization of the chaos of the motion with Lyapunov exponents?
No, just a really great suggestion that I think I've talked to you about in the past. So a fractal basin does actually convey the chaos of the system very well, though.
Yeah.
Lyapunov's is generally accepted as the most defining trait of chaos.
Yeah.
That's true, but it's pretty obvious it's chaos. So like,
no, I just wanted to like ask, because like you can look at the temporal Lyapunov exponent to characterize which phase of the motion is chaotic and which phase is transient chaos versus which phase is non-chaotic. I think that would be a great way to look into the motion of the pendulum more, because I think there is still a bit of limitation with the endpoint analysis here.
Yeah, I think that's something that Kriya did, which is very interesting. So the endpoint chaos in each stage of the motion. So the endpoint chaos, so the transient cases chaos plays into endpoint chaos, obviously.
Yeah, obviously. Yeah.
Okay.
Sounds great. I want to go into a couple of other things. Firstly, oh my, I accidentally closed my document. But can I ask, do you agree that like the B field expresses a torque on the magnet over time, and especially because in the two magnet case, the B field might look a bit irregular, that like the magnet like needs it might not always be in the direction aligning with the B field, or do you think that it's fast enough to react?
So personally, like my personal opinion is that this is a valid assumption, because as I've mentioned, like the Lorentz force only matters when you're in a place with a high B field density, right? Because that's when the Lorentz force is actually strong and has an effect on the pendulum motion. And when the B field is strong, what you're going to have is a very strong magnetic dipole torque that's trying to align the magnet with the B field. So alternatively, we could use a double pendulum simulation to kinematically solve for the orientation of the magnet. However, Okay, so our simulation is running very slow. It takes
Yeah, absolutely. I understand computational limitations as I've experienced them myself. But yeah, okay. That sounds great. I think I might place a little bit more value on the time it takes for torque to correct itself, or the time it takes the how the torque might oscillate. But like might oscillate the magnet's rotation. But we can agree to disagree here. I want to talk about a couple of additional things. Do you think there's any additional like fricative errors with the pendulum? Because obviously, like
Vicious?
we don't have two free joints. Like I want to hear how you attach your pendulum to its mount point, and how you I saw like a black mass on the point, like on the pendulum magnets. I wondered what that is.
Okay, so the black, I'll start in reverse order, I suppose. So the black mass is just a tiny bit of Sharpie that makes the tracking a lot easier, right? Because you have a white background.
Yeah.
So having a high contrast there really makes the tracking easier. As for how we attach it, so we actually tie the fishing wire to the suspension system. And you're right that this does actually cause an effect. So because the point is non-symmetrical, we observed that the effective length of the pendulum is actually longer, very slightly longer in the X direction than the Y. And this, in an FFT, this is quite clear. I really shuffled an FFT. I'm slightly regretting that now. But you see two peaks that are very close to each other, like roughly 0.02 hertz away from each other. And this is the effect of the joint, as you mentioned. Yeah.
Okay, yeah, that sounds great. I just wanted to account for that because, there's obviously fricative errors with any experimental setup, but you sound like you taking that into account when building it. I offer a suggestion though with your thing about magnetic strength, because I thought about that during my own experimental setup. Have you considered the possibility of adding a dead mass to the end of the pendulum so that you're able to model a weaker magnetic strength while keeping the same mass, or a stronger magnetic strength? Because obviously we don't have like infinitely different many strength magnets.
That's a very good point. So I kind of glossed over this in my presentation, but changing the magnet strength, there's actually quite a few issues. So you're also changing the effective length of the pendulum. You're also changing how high above the magnet is from the magnets on the base. And while these might seem small, the magnitude of these changes in relative to their values is actually quite large.
So absolutely, yeah.
3 centimeters height of the pendulum.
Yeah.
So move one magnet that goes to like 4 centimeters.
Do you think it would be still possible to correct for this though? For example, like sandwiching the magnet in the middle of like where you would put the dead mass, or like correcting for the string length height based off of that. I think it'd still be worthwhile to consider. I think magnet strength is a very important thing to experimentally verify, right?
Yeah, I think one data point is quite sad. So what we could have done is that we could correlate we could make multiple variables independent and change them together on this graph, right? So it'll be more messy and less physically significant, but it'll definitely be something that we could look into.
Yeah, that sounds great. Can you go to slide 36? I want to ask about like a deviation from your experimental to your theoretical, because I saw you generally have very strong correlations with your theory and experimental. I just wanted to ask about that.
Sure. Okay. So you're talking about how a theory essentially rises a bit before the experimental does, right?
Yeah.
So this is quite curious for me too, actually. So I looked into this, and to be honest, I can't give you our simulation calculates the amplitude of the oscillation almost perfectly. So what I'd expect to happen is that the frequency, because the centripetal force increases as the amplitude decreases, right?
Yeah.
Plus the frequency to increase. I honestly expected this fit to be better, but I think the issue here is likely. So how we're doing this is that we're running image recognition on a spectrogram, which is a bit low tech. So what recognition does is that it gets the highest intensity pixel on the spectrogram per column, and it takes that as the frequency.
Yeah, I understand, because that's one of my things. Again, initial question relating to your experimental setup here is how do you account for depth within your thing? Because you sort of glossed over the you're solving for the position of the magnet. How do you account for depth, and do you consider there to be any issues with camera warps? Because I'm not particularly sure of your variables. I don't know what your FOV is and where your magnet lies with the FOV.
I did kind of gloss over my trigonometric transform. So essentially how we get the 3D position from a 2D coordinate is that you can think of the pendulum's possible range of motion as a hemisphere. The suspension, right?
Yeah.
So we map our pixel plane. So a ray from the pixel plane, it will only ever intersect once with this hemisphere. So that's how we calculate the 3D position of the pendulum.
Okay, sounds good.
As for camera,
Do you think the rotation of the pendulum affects like your tracking software or where the center of mass would lie?
okay, so I don't think so because when you rotate it, it becomes an ellipse, right? And what we're doing is that we're averaging.
No, but remember, your Sharpie is like from what I recall, it looks like a cone. So when you rotate it like this, you're actually putting the center of mass off center. No.
Well, you'd have to have quite a large rotation for the cone to have an effect on that because if you do like the geometry, it first becomes an ellipse, right? And the ellipse would still have accurate tracking.
I'm not so sure of that, but I think we can agree to disagree. I think the math here would be quite complicated to work out, but because I think the cone's like angle is like quite high. That was one of the things I was curious about the experimental setup. Yeah. Again, I think that's rotational dipole. Yeah. Do you want to go over your frictive forces? Because you glossed over that pretty quickly, but I would love to hear your understanding here. Because for me, I didn't consider a turbulent flow because I thought the Reynolds number for the system was quite low because the velocity of the pendulum was not.
You're right that the turbulent flow is quite low, but we did just take that into account. So unfortunately, we do have to fit all of the fictitious the drag constants, right? Because you can't really determine that.
It's not so easy. Yeah, absolutely.
Yeah, so it's that we fit the velocity to 0. So the Coulomb resistance, the laminar, turbulent, and turbulent is quite slow.
Quite low. Okay, yeah. Can I ask? Because obviously we know that drag is proportional to like cross-sectional area. Do you account for that in your theory, or do you roughly assume it's the same?
Roughly assume it's the same. You're right that as the pendulum rotates, this could have small effects on the cross-sectional area, but it fit well enough.
Okay, yeah.
It's like we just assumed that.
Yeah. Sounds great. Yeah. I think that there's again we could go into like some very great discussion about the chaotic properties of the motion. But one last thing I want to get to is wait, what was the one last thing I wanted to get to? Oh yeah, the pendulum motion itself.
Sure.
Do you think that it always embodies? Because I'm not personally so sure about this. But again, I model as a rigid body. But do you think it behaves like a rigid body at all times, and do you think it behaves like a point mass? Because everyone's magnet sizes and lengths are different.
That's a very interesting question, actually. So about the rigid body.
Yeah.
So, obviously, we assume that the string is a rigid body, right?
Yeah.
So because none of the forces point in a direction upwards on the z-axis, there's no force trying to collapse the string, so shorten the string. So I think that rigid body approximation is quite valid in this case, yeah.
Okay. Do you think the rotation of the magnet can cause some weird cases where the string doesn't like, because obviously it's not again a perfectly free body, it has a Young's modulus. Do you think it could cause where the rotation of the magnet pulls the string in a super nonlinear way?
So how we connect the string to the magnet is that we have a hook, right? So the speed of motion of the string is actually quite high on the magnet. So the shape of the string doesn't change much at the end point of the magnet. But, yeah, there's definitely a lot of these like smaller order, larger order effects that we didn't take into account.
Yeah, because like I think these are valuable because in a chaotic system they can always have an impact. Yeah.
Yeah, definitely. Yeah.
Okay. I think that's time up.
Sure.
Fantastic. All right. Now let's move on to the next stage. So it's the opponent summarizing the discussion.
Thank you. We had a fantastic presentation here. Absolutely amazing. I think we had a very valuable discussion as well. We talked about experimental verification of the data, looking at the chaotic motion of the pendulum as a whole, and whether or not like we can model it using Lyapunov exponents or other ways. We looked at the B-field's torque on the pendulum magnet over time, and just disagreed a little bit on the effects of that over time. We also looked at magnetic strength verification, looking at the correlation between the theory and the experimental for 2 magnet cases. But obviously, again, those are harder to explore just because of the chaotic nature of the system. We also broke down some of the various factors of the experimental setup, including things like keeping track of like camera warps or looking at how you derive the position of the magnet, as well as looking at sources of error like how you attach the pendulum to its mount point and how you attach the magnet to the pendulum point, to the pendulum itself. Overall, I think that was an absolutely great discussion presentation. I applaud the reporter.
Okay, time's up. So now let's move on to the next one. It's time for the reviewer to ask the opponents and reporter questions.
Would you like me to screen share again, Mr. Reviewer?
Yeah, sure. I think that'd be good.
Sure.
Okay. While you're screen sharing, I had a question about your models with one magnet. So I was wondering if you had tried to like model a simulation or something with a magnet that is off center, that is not like directly below the pendulum.
Yeah, our simulation does run that. However, we didn't investigate that as a case because what essentially happens is that the potential host, sorry, that's not the potential host slide. The potential host just gets shifted to the side and effectively the same behavior occurs.
Okay. So regarding your simulation, how exactly was it formed? Like, is it based on the data points and then animated, or is it an entirely separate simulation with variables?
That's an interesting question. So our simulation, so we have three main parts. We have a module that calculates the B field and Lorentz force, and then we have a simulation that solves the ODE of the pendulum. So what the ODE is that solves for the angular accelerations at any given condition.
Were you able to incorporate a damping coefficient into the simulation?
Yeah, absolutely. So as I mentioned, we characterized all of the relevant dampings, which include the eddy.
Okay. Yeah, I got it. So have you considered things like Poincare systems or bifurcation for defining chaos?
A bifurcation as a chaos. No, the only method of chaos that we looked into was the fractal Bayesian. The next step could definitely be Lyapunov's exponent, as that's slightly more quantitative. But fractal Bayesians is quite obviously chaos, right? So.
Yeah. Regarding your discussion on like gravity creating a hill, so could you like expand on that a bit?
Sure. Unfortunately, I started running out of time, so thank you very much for asking this question. So if you look at this in an energy perspective, what you get is this potential Ho diagram. Is that as you move the magnets apart, eventually there's a third attractor that emerges. So what an attractor is this dip in the potential. Well, gravity is always an attractor, but it emerges as an important attractor that forms a third stable state that the pendulum can end in. Because all of this, the stable state is defined by a dip, a potential valley in the potential Ho.
Okay, yeah, sounds good. So how did the damping impact the system's trajectory?
Sure. So the damping, okay, so if you have a stronger damping, it will just reach the end state faster in all cases. But
yeah, so like did you notice any like impacts on trajectory specifically?
On trajectory, so it will change how the magnetic basin looks because it's very chaotic. But it will also increase the stable size of the regions, stable regions. Yeah.
Sorry, time's up.
Okay.
Okay, so let's move on to the preparation phase for the reviewer. So take your time.
Okay, we take a break. Oops, sorry, I'm unmuted.
You're not muted.
10 seconds left. The reviewer should start putting on the slide.
Okay, so I think this was a very important, good discussion between the opposition and the reporter. So for this problem, yeah, we already know the problem. So for the tasks that we valued most, it was the experimental setup, which was done well by the reporter. They had a clearly explained setup, and they did, in fact, identify most of the key parameters. As for the development of the theoretical model, it was also done well with the explanation of the motion governing physics for their framework that predicts behavior. And then for the experimentation, of course, their procedure was done well. They had cameras that they took everything into consideration, and for their conclusive results, they're able to align it with what they noted. So in their theoretical analysis, they discussed the B-field model, the Lorentz force, Basins, and for the experimental confirmation, they had a simulation. So some merits to the reporter is, of course, the characterization of forces, where they were able to consider magnetic torque, which is something that we actually missed, along with several other forces in a completely separate model. And then their theory was also impressive with equations of motion such as Runge-Kota-Filberg, which is an extremely non-incredibly complicated thing to analyze, as well as B-field, surface current, and model, as well as accurate computer vision tracking and computational theory. And for the next steps, we wanted a more quantitative consideration of damping coefficient because we felt that although we could see their impacts, although we could see their impacts in terms of patterns, we cannot see a proper path, as well as an experimental verification, as there was only one case with the verification, as well as more endpoint, star point analysis for motion in between. So the key insights of the opponent was Lyapunov chaos theory, the magnetic strength verification, and the correlation between theory and experimental. So for the opponent, their merits were, of course, the mentioning of damping, as well as torque over time, and of course, their consideration of the Lyapunov exponents and the discussion of the experimental setups. Although for possible next steps, there could be clear points from their pacing of speech, although they were very passionate, and the relevance of questions as the camera warps we'll soon see are not necessarily the most relevant to the discussion. So regarding the camera warp, the point raised by the opponent was that it may not be constant, but the reporter's response was that it was negligible, which we agree with, as given the angles and 3D model of the reporter, as well as all the considerations that were made to pretty much minimize any inaccuracies, we felt that this also was negligible. Now, as for the Lyapunov analysis, the opponent raised that it is the most conclusive indicator of chaos, while the reporter's response was that it is already very clearly in chaotic motion. And although we agree that we can see from the basins that they're in clear chaotic motion, we still felt that the Lyapunov exponent is still the most conclusive because there are still textbooks, researchers that still argue about the concrete definition of chaos. And the Lyapunov is one that is able the Lyapunov exponent is the one that is most able to is the one that is the most concrete in terms of defining the incorporation of chaos in between endpoints. Now, as for magnet strength, point raised by the opponent was that we can add den mass to the magnet to increase the mass while impacting the strength minimally, while the reporter's response was that there are quite a few issues with the magnet strength and many parameters. And we, however, do agree with the opponent that magnetic strength will be an important consideration, also since we only consider the one data point. Now, as for missed physics, we felt that experimentally it was slightly lacking. With the experimental derivation of the damping coefficient being minimal and not sufficient to how important we need damping.
Time's up. How many slides do you have left?
That is all. Thank you.
All right. Cool. Let's move on to the next stage. So now it's the reporter coming over to give a summarization.
Sure, thank you. That's me. So first of all, I guess I'll start with thanks too, as it's classic. So I had a really intriguing discussion with the opponent. It was very fruitful. We discussed honestly a lot of interesting points that I explored outside of the presentation, but didn't have time to get to in my presentation. Most notably, the non-symmetry of the binding, which, as I mentioned, produces these beats that you see in the data. Otherwise, we also demonstrated, so regarding one of the reviewer's points, we did actually demonstrate the endpoints, starting points, and all of the points in between in my presentation. We investigated both the chaotic regions and the stable regions using the animation and changing the animation's initial condition. Otherwise, maybe I'll just do a quick review of my report. So I simulated my magnets using a volumetric simulation, so using ground currents. And then after this, we solved for the equations of motion of the pendulum using Euler-Lagrange, and then integrated that using Runge-Kutta. We explored fractal basins. So one of the points that often came up was that perhaps Lyapunov's exponent would have been a better choice to characterize the chaos. And we agree, although fractal basins also has its own unique set of benefits that we believe that we should address here. So fractal basins really let you visualize how the chaos emerges, especially when changing parameters. Lyapunov's exponent is great as a quantity that the Lyapunov's exponent is positive, it's chaotic, but fractal basins really show you what's happening in the system and why it's chaotic. In this case, being the higher energy states having more time to have transient chaos appear. Sure. And then lastly, we also investigated numerous parameters, both across the single magnet case and the double magnet case. In the single magnet case, it came up both for the reviewer and the opponent that perhaps we could include more data points in our magnet strength versus oscillation frequency. We discussed this pretty in depth, and it would be great to have more data points, but there were limitations as we discussed. Thank you again to everyone for the very fruitful discussion, and that's it.
All right, great, fantastic. Now it's time for the jurors. I believe you guys definitely have a lot of questions to ask. So if you have questions, you may just go first.
I have a question. So, reporter, can you go back to slide 35? So there, I saw some.
Sorry, 35, I believe, is over here. Yeah.
Yeah, I see some oscillations. Can you explain that?
Sure. Absolutely. So how this works is that essentially our camera tracking is actually slightly off center. So because our camera is slightly tilted, like a tiny amount, 0.1 degrees or so, what happens is that's not oscillating around the absolute center point of the magnet as it's oscillating. So because of this, we do see some oscillations. So apparent observation oscillations that are actually fictitious. They're not actually in the system.
So they're artifacts, basically.
Yeah, they're artifacts of the tracking.
Can you think of an experimental setup where you can minimize this?
Sure. It'll just take more camera calibration, really. So it's just that we often had to take the camera off and on. So if we calibrated it better before each shot, we'd remove these oscillations effectively. Yeah.
Okay.
I have a question. Clara, do you have any more questions? No?
You can go ahead.
Okay. I'd like to ask on your integration, Runge-Kutta 8-9. Is there a particular reason why you chose 8-9 instead of the standard classic 4-5?
So ultimately, because one second, let me go to the actual integration slide. I went to the wrong one, I think. So what we saw is that because the time length of our integration is so long, it's often hundreds of seconds. 4-5 had some inaccuracies that started building up, and we saw that 8-9 gave better results. We just tried both of them and saw that 8-9 had better results for us. So yeah.
Like, did you also try reducing the step size for both?
So because this is an adaptive solver, it changes the step size based on the like Feldberg method is adaptive, right?
Mm-hmm.
So they're both adaptive solvers. So you can't really change the step size.
But there is like a way. If you do the regular Runge-Kutta without the Feldberg addition, you can deliberately choose a small step size.
Yeah, exactly. Yes. Mm-hmm.
Like, did you code this in Python or MATLAB?
Yes, this was in Python. So
okay.
Using
the SciPy package?
Yeah, exactly. The SciPy ODE solver. Yeah.
Okay.
Mm-hmm.
Nope, that's it. No other questions for me?
Sure.
I just want to suggest one thing. So if calibrating the camera is, going back to my original question, if calibrating is hard, you might want to take some background measurements if that's possible, so you can subtract the background if that's.
The calibration issue is because It's because the camera is slightly tilted, right? So here you can see that the camera is mounted on a tripod, and it's very slightly tilted, very small degree, but it's possible to fix it. It just takes more time, and I was a bit lazy.
Yeah.
Thank you. Mhm.
I could ask a couple quick questions. First off, for the opponents, could you just like as briefly as possible describe or define chaotic motion?
Initial state sensitivity. So a small change in the initial state yields a large change in the trajectory slash endpoint.
Awesome, thanks. And okay, for the reporter, maybe I missed it. Did you play around with the initial conditions of the experiment, like when you're, I don't know, the initial angle?
Yeah, absolutely. So the thing that the fractal Bayesian represents, so each of these pixels is an initial angle of the pendulum.
Okay, right. And so this is all from simulation that you get this from?
Yeah, every single pixel we simulate across time.
Right. And the experiment was what? Do you have like regions in here that correspond to the experiment that you did?
Yeah. So sorry, I interrupted a bit, but in the experiment we also see that there's chaotic regions and stable regions. The stable regions just represent where the magnet goes directly to the magnet on the bottom. We then quantitatively compare experimental and theory, because what we're doing here is that we're analyzing the parameters. And we believe that we already sufficiently experimentally verified our model to be able to just have fun and theoretically analyze all of the different parameters and how they affect the chaos.
So, yeah, okay, great. Thanks a lot.
All right, so we're done. Now we're on time. So maybe you guys can just submit the thing to my folder, and then we will take a bit of break for the committee to start counting the marks together and then decide who's the winner. And also, in the meantime, like the jurors can also submit to me your nominations for the best theory and also the best experimental setup awards. So all you need is just to write me the names of the person you think that's eligible for this award, and we will look over and the score sheet. All right.
Okay, I've uploaded.
Great. I'll count them towards the mark now.
I uploaded.
Side question to the enemy, sorry, opponent. Why are you wearing cat ears?
I have uploaded my.
We might have dared them to do it. Team Shrimski's not
Our team name is Schrodinger's Cat Girls. So before the presentation, we flipped a coin to see whether I'm a cat girl or not. So this is just a bit of fun.
Also dominated by Team Shrimskis.
Wait, hold up. Are Shroomskis and cat girls are in the same room right now?
No.
No.
The thing is, I just want to put it out there that we had a majority decision on a team named Skibidi.
Oh, you silenced them. Okay.
Fantastic.
Yeah.
I heavily apologize for my teammates.
I didn't do that. They silenced themselves, I think.
Yeah, I know. Jeff, are Shroomskis and the cat girls the same school?
They are from the same.
Yeah.
Okay. Now I
okay.
understand.
That explains a lot, right? Like
That explains a lot because it's as if they saw each other's presentations before. I'm like, you know this, you know that, and like, like
to be clear, we haven't seen each other's presentation, but we did discuss some things initially about the theory.
because it felt like, you know, what's that thing called, match fixing, the illegal thing where
Oh, is this an accusation?
No, please don't disqualify us.
It's an internal battle,
No,
internal war in the school.
we didn't discuss the problems. Well, we discussed the problems, but not our side.
Louis, if you're going to lie, try harder.
No, legitimately, we did not discuss anything about the slideshow. I cried about simulating double pendulum, so we talked a little bit about the double pendulum and the Lyapunov's exponents. But
Both of our teams have contract with secrecy now.
Oh, I can.
my days, bro.
Actually, I can verify that because they invited me, like not invited me, but essentially like, they never actually show each other, like even though they're like presenting within their school. So fun thing. Okay, so I got majority of the score sheets. So I still need one more.
Jeff, are you also from UTS?
No, I'm not. I'm not from UTS. I don't know them before last year.
Okay.
Yeah. And they're just random kids.
Yeah.
Okay. So I just need one more. All the scores have been punched in. Yeah. Oh, all right. I got all the scores ready. All right, so let's take a bit of break. I will get the slideshows ready, and then let me look at the schedule 1 second. And when we're back, we'll just start our awards ceremony. And that should be... Oh, we end perfectly on time, 7. And we'll have a break for half an hour, and then we're working on this. And at 7:30, we'll start our award ceremony, which is going to be rather quick, so we can have our dinner. So yeah, in the meantime, you guys can like just maybe chill in this Zoom room for a bit, and then we will see each other right soon.
Just a curiosity, Team Shumskis and the Schrödinger cat girls are from the same class or just the same school?
Same school, they're of different ages.
Ah, okay. Okay, so there is no risk.
I mean, they probably see each other every day or something.
Ah, right.
Yeah.
I don't think
because
they see each
that's
other
the
every day.
sense I got. I mean, obviously, I'm not accusing them for anything, but like when they were like, they were not attacking each other. They were very friendly, which is very weird in the finals. Like usually in the finals, everyone has their knives out.
Wow.
Yes, exactly.
Yeah.
And it was like,
Maxwell's demons would be extremely grateful if there was an investigation carried out.
Investigation.
From which school Maxwell Demons comes from? Which region?
We're from St. Robert's. It's near Richmond Hill and Thornhill.
Ah, okay. While Chomsky's and obviously Schrödinger Catgers.
they're from University of Toronto schools downtown.
Ah, okay, wonderful.
Although not anymore. Yeah, not anymore.
What do you mean not anymore?
Our school dropped out, so we're doing it independently this year. So.
Ah, okay.
Is it the teacher that we all know?
Possibly.
Possibly.
Are you being advised by elder students who passed through CaYPT before.
Yeah, we've had a lot of help this year from a lot of like Hong Kong, Korea. Had a lot of fun sources. Yeah, it's been fun.
Mhm.
I miss it when it was live, I remember. When it was in Waterloo and also in downtown Toronto, U of T. Like everyone has their knives out and they're like it's like in court.
The only Waterloo one was the very first one in Perimeter.
Yeah. Like they were like their knives out, amazing.
Yeah, I miss it too. Live is a lot more fun than online actually. But oh well. Maybe next year.
Okay.
Oh, Jim, can you join the comedy voice chat? I So, hey guys, the award ceremony will begin in 1 minute. So, yeah. All right, so I suppose we can begin. I hope everyone's back in front of the computer. So here we'll begin our calling it end of the year to 2025 CaYPT with an awards ceremony, and we're here to appreciate everyone's commitment, their efforts, and also achievement they have earned in the tournament. So to begin with, we're going to have our Best Experiment Awards. This is an awards given to the experimental setup that's the most rigorous, most comprehensive, also the most considerate. And it's given to those who have put a lot of efforts in iteratively designing their experiments. And this award is given to the person that's decided by the jurors collectively. And of course, this is not just the finalists, but it's throughout the entire tournament. So this Best Experiment Award is gonna be given to Daniel Cui, which is from Team Schrodinger's Cat Girls, which is one of the finalists we just seen just now, with his experiments on the ruler cannon, and his design is considered as a very great experiment, and therefore we give them the Best Experiment Award. So is Daniel here? Don't tell me he's not here.
Yeah, I'm here. Hello, sorry for the background. We're in the restaurant.
All right. Okay, just to tell you, you got the Best Experiment Award, and you should be happy about it. All right, great. So let's move on to the next one. So we have the Best Theory Award. So this award is given to the theoretical model that's considered that as most amount of aspect as possible. It's very demonstrative, interpretive, as well as very accurate scientifically. And even the limitation of this theory can be fully explained by the presenter himself, and also it has a very good visual demonstrations of the phenomenon. So I believe those who have been to finalists should know who earns this award. So this award goes to Lu Yu Wu, and from Team Struski, who is also one of the finalists today, and his pendulum with magnetic and also his rim magnets models earns the Best Theory Awards. So Louis is here, right?
Yeah, thank you so much. We appreciate it. Yeah.
Okay.
No, Elaine should have won this. Yeah, but thank you. Yeah.
Thanks all the jurors because they collectively voted you guys out. And, yeah.
Thank you so much. Yeah.
All right. And next, we actually have a special awards that's not very scientifically oriented, but it's a very teamworking oriented. So which is called Mohammed Asadi Lowry Leadership Awards. So this award has a very special meanings behind, and the name, and this award is named after the founder of CaYPT and the one who brought CaYPT from Iran all the way to Canada. And this award is actually in memory of this person who's also the founder of STEM Fellowship, of course. When he passed away in an airplane accident a few years ago. So this award is just given to those who demonstrate leadership throughout the tournament and have tried to get the teams together to try their best. So this award, as decided by the committee, is given to Xuejin Yang from Team Google Blitz for the leadership awards. Are they here?
Hi, yeah, we're here.
All right. Okay. All right. So I guess we move on to the next awards. I guess it's the ones that we start moving to the main dish of the bronze, silver, and gold. But before that, we start with the participation awards to appreciate those who have worked extremely hard throughout the tournament and have dedicated their times throughout. So the first team is the Team Jewel Thieves from Appleby College. We sincerely appreciate the time and effort you have devoted to this tournament this year. And the next one is Team Buffalo, 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 Buffalo. And your efforts is being recognized, and we sincerely appreciate that. And we also have Team Kugelblitz. It was just an independent team, not from anywhere. And we sincerely appreciate your efforts and your commitment throughout. And the next one is Team Women in STEM, which is from Victoria, British Columbia, the only team that's not from Toronto. We appreciate your efforts and wish you best luck. And the next team is Team DMCI Higgs Bosons. They're from Team Domuse Collegiate Institute in downtown Toronto, not downtown Toronto, but in Toronto. And yeah, we appreciate your efforts and commitments throughout, and wish you best luck. And if you will try out for individual team, and yeah. So moving on, we have the list of bronze medalists who are going to win, of course, win bronze medals. So the way how medal works is that half of the team will get will be considered for bronze medal, and then okay, so for this year it's like 2 bronze medal, 2 silver medals, and 1 gold medals. So the 2 finalists will get silver medals, and the winner will get the gold medal, and the top 5 with the 5th place and the 4th place will get the bronze medal. So we're moving on to the 5th place we have here is Team Schrodinger's Revenge from Appleby College in Oakville. And they have demonstrated great teamwork throughout the tournament, and congrats them for earning a bronze medal. Okay. Moving on, we have the next team, which is Team Physics in Style, which is independent teams from North York, Ontario. They have also won a bronze medal, ranking 4th place, very close to the final. And wish you all the best luck. Maybe you guys would try out for national camps. And yeah, congratulations for getting a bronze medal. All right, I guess that's the most exciting parts here. We get to announce whoever wins in the finals. And I'll announce by 3, 2, 1. So it's a 3rd place first, 2nd place, and then 1st place. So we begin now. So the 3rd place of the 2025 Canadian Young Physicist Tournament goes to Team Maxwell's Demons from St. Robert's Catholic High Schools on Toronto, Ontario. They scored a final marks of 41.71. That's extremely high marks. And with Team Maxwell's Demons want to say anything, and we sincerely congratulate for winning the silver medal this year. Are they here?
Oh, we're here. So we'd just like to thank the organizers of this competition. We'd like to thank Jim, you as well, Jeffrey, the jurors, the chairs, the volunteers, and the participants, the competitors, especially coming out on like a weekend. It was an honor to be a part of this competition, and we just like to thank our competitors. And I hope you guys have a great rest of your night. Thank you.
Thank you. All right. So the next team, I guess it's the most like stressful one here. So this is the 2nd place. Essentially, when we say who's the 2nd place, we know who's the 1st place is, of course. So the 2nd place of the finalists goes to Team Schrodinger's Cat Girls, which is an independent teams from Toronto, Ontario. They have a final score of 47.21, and it's a very high mark. And would the team captains and the teams say anything else? And congratulations for getting silver medal in 2nd place.
I know it's very loud here, but I would like to quickly thank everyone, the jurors, all my teammates, and Jeffrey and Jim for organizing this tournament. Thank you so much.
All right, enjoy your dinner, and hope you guys would like the silver medals. All right, so now I guess the gold medals, which is the 1st place of the tournament, and undoubtedly it goes to Team Shroomski, which is an independent team as well from Toronto, Ontario, and they have a final score of 49.71, which is an insanely high marks. And if you go to CaYPT, you will never ever see that score unless it's performed by Singapore. But yeah, congratulations for getting the 1st place and also the gold medals. So do you guys want to
have any thoughts or anyone you want to say?
Our camera looks diabolical right now, but do you guys want to share some thoughts?
Okay, I guess I'll start. I just want to really thank, like, of course, mirroring the statements for other people, like the jurors who took time out of their Saturdays to help the competition, like jurors ask us insightful questions. I'd also like to thank the participants for such like fruitful discussion. It was such amazing interactions and got to meet so many people along the way. So yeah.
Absolutely. I think it was a very fruitful competition overall.
Very fruitful experience.
Yeah.
For real.
I had tons of fruit.
Really commendable.
All right. I can feel the joy through the screen. But all right, enjoy the gold medals and wish you guys have a great night. And yeah, so that actually sums up our 2025 Canadian Young Physicist Tournament. And I sincerely appreciate every volunteers, every jurors, and every chairs, and also all the organizers that are involved, and as well as all the participants that we devoted their times throughout this entire tournament and gone through these 2 weeks of long tournaments. And essentially the time that we put, like the time everyone's here put, is actually more than 2 weeks. It's actually like starting all the way from last December. So yeah, thank you all for participating in this year's CaYPT 2025, and wish you all the best luck and see you all next year.
Thank you so much, Jeff. Thank you so much to everyone, and have a good night to everyone. Thank you so much. Congratulations to all the teams. So see you next year. Bye.
Thank you,
so
Chair.
much.
Thank you.
Thank you.
All right.
Thank you.
Thank
you guys.
I thought that was like a background music for a winner.
I think that's yeah. We should get some the background music.
Oh yeah, definitely should get that next year. Wow. Okay.
Wait, they should just start playing the elevator.
All right.